Hello and welcome to this revision session for AQA A-Level Physics, where we're going to be looking at the topic of mechanics and in particular Newton's laws and momentum. So if we've been successful and we've learnt in today's lesson, we should be able to answer A-Level Physics examination style questions, assess your understanding on A-Level Physics and understand what topics we need to improve upon for A-Level Physics. So how should you prepare for this revision session? When you complete your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and in this left hand side section write down your working out and answers to the questions in the revision session. When you're doing this, make sure you write in full sentences and show your full working out. What's in the right hand side, write down any piece of information which you find useful or any hints and tips on answering the questions from this revision session. After the end of the revision session, write up these notes into a revision sheet for you to use independently. Now, how can you revise AQA A-Level Physics? So, first step is to learn the key facts. Use revision guides, class workbooks, student prep notes and a textbook to learn the key ideas of the course. Now, you may wish to make mind maps or to write out the notes yourself. The second step is to test yourself. Use things like Caboodle, Seneca, student knowledge checkers to quickly test your own knowledge, and you may wish to do this from your own cue cards. The third step is to practice exam style questions. Use exam prep books, homework books, study books, additional workbooks to answer exam questions and mark your own work. Now you may wish to download your own exam past papers to do this. So learn the key facts, testing yourself and practicing exam style questions are how you can revise AQA A-Level Physics. Now in today's revision session we're going to be looking at two types of questions. The first are general questions, which are the basic questions designed to probe your understanding of the concepts of the topic. Then we're going to look at assessment point questions, which are past paper examination questions which will mimic the types of questions found in public examinations. So let's have a look at these general check questions. The first question is, what is Newton's law of motion? So pause the video now, then unpause the video when you want to go through your answer. So it is, an object will only accelerate when a resultant force acts on the object. What is Newton's second law of motion? Pause the video now, then unpause the video when you want to go through your answer. It is when the acceleration on an object it undergoes is directly proportional to the resultant force acting on the object and inversely proportional to the mass of the object. The next question says, what is inertia? And explain your answer using Newton's first law. So pause the video now, then unpause the video when you want to go through your answer. Inertia is the property of an object that resists change to its state of motion. An object with a greater mass has greater inertia and requires a larger force to change its motion. Newton's first law of motion states that the object will remain at rest or in uniform motion in a straight line unless acted upon by an external force. This is also known as the law of inertia. The next question says, Zola is playing hockey. The ball is coming towards her at a speed of 4.6 meters per second. She hits it so that it travels in the opposite direction at a speed of 10.2 meters per second. Her stick is in contact with the ball for 0.84 seconds. The ball has a mass of 161 grams. Calculate the average force exerted on the ball during this time. So pause the video now, then unpause the video when you want to go through your answer. Well, acceleration is the change in velocity over the change in time. So it's 10.2 minus 4.6, because it's now moving in the opposite direction, so it's now a negative, divided by 0.84. So that is 14.8 over 0.84, which is 17.619 meters per second squared. F equals ma, so it's 0.161 grams into kilograms, times by 17.619, so equals 2.84 newtons. The next question says, a rocket burns through its fuel stores to accelerate upwards. Explain why you can't use F equals ma to calculate the net force on the rocket in this case. So pause the video now, then unpause the video when you want to go through your answers. So, the rocket is burning through its fuel stores, so it's losing mass in the form of fuel. F equals ma cannot be used as it requires the mass of an object to remain constant. The next question says, a car is pulling a caravan behind it at a constant speed. The additional resistive forces acting on the system due to the caravan at this speed is 780 newtons. The link between the car and the caravan breaks and they separate. The car immediately begins to accelerate at 0.41 meters per second squared. Calculate the mass of the car. So pause the video now, then unpause the video when you want to go through your answer. So we know m equals F over A. M will therefore equal 780 over 0.41, 1,900 kilograms. The next question says a train engine of mass 5 tons is moving along a straight track with a constant acceleration. In an 8-second period, it covers a distance of 250 meters, at which point it has a velocity of 25 meters per second. Find the acceleration of the train engine and find the resultant force on the train engine. So pause the video now, then unpause the video when you want to go through your answer. Well, we know s equals ut plus a half at squared. We can use this as this constant acceleration. So 250 equals 35 times by 8 minus a half times by 8 times by 8 squared. So a will equal 0.9375 meters per second squared. F equals ma, so it's 5,000 tons into kilograms, times by 0.9375 is F equals 4687.5 newtons. The next question says, what is Newton's third law of motion? So pause the video now, then unpause the video when you want to go through your answer. Well, when two objects interact, they exert equal forces of the same type and magnitude on each other in opposite directions. The next question says, is the following situation a Newton's third law pair and why? So pause the video now, then unpause the video when you want to go through your answer. No, they are not, as both forces are acting on the same object, so it can't be a Newton's third law pair. So, what law does this situation demonstrate? So pause the video now, then unpause the video when you want to go through your answer. Well, this law is demonstrating is Newton's first law of motion, because there's no resultant force on the object, so it's not leading to the object accelerating. The next question says, is the following situation a Newton's third law pair and why? So pause the video and then unpause the video when you want to go through your answer. Well, yes, it is. The two forces are equal in size, they're opposite in direction, they're of the same type, and they act on different objects, so they're a Newton's third law pair. Is the following situation a Newton's third law pair and why? So pause the video now, then unpause the video when you want to go through your answer. Yes, it is. The two forces are equal in size, opposite in direction, are of the same type, and act on different objects. Is the following situation a Newton's third law pair and why? So pause the video now, then unpause the video when you want to go through your answer. Yes, it is. The two forces are equal in size, opposite in direction, are of the same type, and act on different objects. Using Newton's third law, describe why when a balloon is untied, it travels in the opposite direction. So pause the video now, then unpause the video when you want to go through your answer. Well, the air inside the balloon will rush out with the force of F1. This will produce an equal and opposite force on the balloon, F2, forcing the balloon to move through the air in the opposite direction. Explain why a swimmer moves forward in water when they push backwards with their arms. So pause the video now, then unpause the video when you want to go through your answer. Well, the swimmer pushes backwards on the water with their arms. The water pushes forward on the swimmer with an equal and opposite force. So this forward force propels the swimmer through the water. A box rests on a table. Identify two pairs of Newton's third law force acting in this scenario. So pause the video now, then unpause the video when you want to go through your answer. There's firstly the box-table interaction. The box pushes down on the table due to its weight, then the table pushes up on the box with an equal force. But there's also the box-earth interaction. The earth pulls the box down with gravity, and the box pulls the earth up with an equal and opposite force. A rocket expels exhaust gases downwards at a speed of 2.5 kilometers per second. Explain using Newton's third law how the rocket is able to accelerate upwards. So pause the video now, then unpause the video when you want to go through your answer. The rocket engine pushes exhaust gases downwards. By Newton's third law, the exhaust gases push the rockets upwards with an equal and opposite force. This force propels the rocket upwards. Why does a bird lift into the air when it flaps its wings? So pause the video now, then unpause the video when you want to go through your answer. When a bird flaps its wings, it pushes down on the air. The air then pushes back up on the bird's wings with the same force, causing it to lift. The next question says, what is linear momentum? So pause the video now, then unpause the video when you want to go through your answer. Linear momentum is a measure of how difficult it is for an object to change its linear motion. The next question says, what factors affect the linear momentum of an object? So pause the video now, then unpause the video when you want to go through your answer. Linear momentum is the product of an object's mass and velocity. The more mass and speed it has, the more momentum it has, and the harder it is to stop. So a truck moving at a high speed has a lot more momentum than a bicycle moving slowly. Explain how linear momentum differs from kinetic energy, even though both depend on mass and velocity. So pause the video now, then unpause the video when you want to go through your answer. Momentum is a vector quantity defined as the product of an object's mass and velocity. It depends on the direction of the object's motion. Kinetic energy, on the other hand, is a scalar quantity defined as a half mv squared, and it depends only on the speed of the object, not the direction. Momentum can change with direction, whereas kinetic energy does not. Discuss how the importance of impulse in changing an object's linear momentum is. Provide an example where impulse plays a crucial role. So pause the video now, then unpause the video when you want to go through your answer. Impulse is important because it quantifies the effect of a force applied over the time interval to change an object's linear momentum. For example, in car crashes, airbags provide an impulse that changes the momentum of a person's body more gradually, reducing the force experienced and thus minimizing injury. How does the concept of linear momentum help explain why it is difficult to stop a fast-moving heavy truck compared to a slow-moving light car? So pause the video now, then unpause the video when you want to go through your answer. Momentum is the product of mass and velocity, so a fast-moving heavy truck has a much larger momentum than a slow-moving light car. Because momentum is conserved and changing, it requires a force over time, an impulse. Stopping the truck requires a greater force or longer time compared to stopping the car, making it a lot harder to stop. Can an object have linear momentum if it is not moving? Explain. Pause the video now, then unpause the video when you want to go through your answer. No, an object cannot have linear momentum if it is not moving. Momentum is the product of mass and velocity, and if the velocity is zero, the momentum is also zero, regardless of the object's mass. Why do seatbelts and airbags make cars safer in terms of linear momentum and impulse? So pause the video now, then unpause the video when you want to go through your answer. Seatbelts and airbags increase the time over which a force acts during a collision, thereby reducing the force experienced by the object. This is because impulse, the change in momentum, is the product of force and time. By extending the time, the force exerted on the occupants is reduced, decreasing the likelihood of injury. Discuss the role of momentum in sports, such as in a football game when kicking a ball. So pause the video now, then unpause the video when you want to go through your answer. When a player kicks a ball, they transfer momentum from their foot to the ball. The harder and faster they kick, the more momentum the ball gains. Determining its speed and distance travelled, the transfer momentum is essential for controlling the ball's motion and its direction. The next question says, why is it easier to catch a slow-moving ball than a fast-moving one in terms of linear momentum? So pause the video now, then unpause the video when you want to go through your answer. A slow-moving ball has less momentum compared to a fast-moving one. So when catching a ball, reducing its momentum to zero requires less force if the ball has a lower momentum. So therefore it's easier to catch a slow-moving ball because it involves a smaller change in momentum, resulting in less force exerted on the hands. Calculate the momentum of a 2 kg object moving with a velocity of 5 meters per second. So pause the video now, then unpause the video when you want to go through your answer. Linear momentum is mass times by velocity, so it's 2 times by 5, so it's 10 kg/meters per second. A football of mass 0.45 kilograms is kicked, giving it a velocity of 25 meters per second. Calculate its linear momentum. So pause the video now, and unpause the video when you want to go through your answers. Linear momentum is mass times by velocity, 0.45 times by 25, which is 11.25 kg/meters per second. A water balloon of volume 4.2 times 10 to the minus 3 meters cubed is thrown at a speed of 8.5 meters per second. If water has a density of 1 times 10 to the 3 kilogram meters per meter cubed and the rubber balloon itself has a mass of 12 grams, calculate the balloon's total momentum. Pause the video now, then unpause the video when you want to go through your answer. Mass is equal to density times by volume. So it's 1 times by 10 to the 3 times by 4.2 times 10 to the minus 3, which is 4.2 kilograms. Linear momentum is mass times by velocity, 4.2 plus 0.012 grams into kilograms. Times by 8.5, it's 36 kilogram meters per second. A 3 kilogram object is initially at rest. It is subjected to a constant force of 12 newtons for 4 seconds. Calculate the final momentum of the object. So pause the video now, then unpause the video when you want to go through your answer. Acceleration is force over mass, so it's 12 over 3, so it's 4 meters per second squared. V equals U plus AT, so we know that it's going to be a 0 plus 4 times by 4, which is 16 meters per second. We can use an equation of motion as there's a constant force on the object. Momentum is mass times by velocity. 3 times by 16, it's 48 kilogram meters per second. A 5 kilogram object moving with a velocity of 10 meters per second is brought to rest in 2 seconds. Calculate the average force exerted on the object. So pause the video now, then unpause the video when you want to go through your answer. The change in momentum is mv minus mu, so it's 5 times by 0 minus 5 times 10, so it's going to be equal to minus 50 kilogram meters per second. We know that force is equal to the change in momentum over the change in time. It's minus 50 over 2 minus 25 newtons. What is the conservation of momentum? So pause the video now, then unpause the video when you want to go through your answer. This is that the total momentum of all objects in the situation beforehand equals the total momentum of all the objects in the situation afterwards. Does the conservation of momentum apply to all situations? Pause the video now, then unpause the video when you want to go through your answer. No, the conservation of momentum only applies to situations where the system is isolated or there are no external forces acting on the objects. Can the momentum of objects in a system change if the conservation of momentum is applied? Pause the video now, then unpause the video when you want to go through your answer. Yes, the individual momentums of an object in a system can change, but it's the overall momentum of the system that must be constant. In an explosion, which object will travel faster, the larger or smaller object, and why? So pause the video now, then unpause the video when you want to go through your answer. Well, the object with a smaller mass will travel faster, as in the explosion the overall momentum is 0, so the two objects have the same magnitude of momentum, just in opposite directions. So as the smaller object has the lower mass, it must have the higher velocity. A trolley of mass 0.80 kilograms collides head-on with a stationary trolley B at a speed of 3.0 meters per second. Trolley B has twice the mass of trolley A. The trolleys stick together and travel at a velocity of 1 meter per second squared. Determine whether it's an elastic or inelastic collision. So pause the video now, then unpause the video when you want to go through your answer. Well, beforehand, we know kinetic energy is a half times mass times velocity squared for A and B. So it's a half times by 0.8 times by 3 squared plus 0, because it's not moving the trolley B. So it's 3.6 joules. Afterwards, it's a half mv squared for the two objects combined. So you add the masses, it's now 2.4, so it's a half times by 2.4 times by the total speed, 1 squared, so it's 1.2 joules. It's an inelastic collision as the kinetic energy has not been conserved. Now state whether the following collisions are elastic or inelastic and explain your answer. The collisions between air molecules in a balloon, a tennis ball bouncing on the ground, and a high energy electron colliding with a metal target in an X-ray tube. So pause the video now, then unpause the video when you want to go through your answer. The first one is elastic. If the collisions were inelastic, the molecules would lose kinetic energy, move more slowly, and the gas would eventually cool down. The second one, it's inelastic. A tennis ball loses height with each bounce, so therefore it loses kinetic energy. And the last one is inelastic. Some of the kinetic energy of the electron is transferred to form the energy of the X-ray. The next question says a railway wagon of mass 8,000 kilograms collides at 3 meters per second with initially a stationary wagon of mass 5,000 kilograms. The two wagons separate after the collision. The 8,000 kilogram wagon moves at a speed of 10 meters per second without the change of direction after the collision. Calculate the speed and direction of the 5,000 kilogram wagon after the collision. So pause the video now, then unpause the video when you want to go through your answer. So, beforehand, it's 8,000 times by 3 plus 5,000 times by 0. That must equal 8,000 times by 1 plus 5,000 times by v, because the total momentum before equals the total momentum afterwards. So it's 8,000 plus 5,000 v equals 24,000. So therefore v is going to be equal, when we work it all through, to be 2.4 over 0.800, which is 3 meters per second squared. With the same situation, calculate the loss of kinetic energy due to the collision. So pause the video now, then unpause the video when you want to go through your answer. In this question, you need to work out the kinetic energy of each object before and the kinetic energy of each object afterwards. So beforehand, it's a half times by 8,000 times by 3 squared, plus a half times by 5,000 times by 0 squared, so 36,000 joules. Afterwards, it's a half times by 8,000 times by 1 squared, plus a half times by 5,000 times by 3.2 squared, 29,600. So we therefore have lost 6,400 joules of energy to the surroundings, so therefore it's an inelastic collision. A vehicle of mass 800 kilograms moving at a speed of 15 meters per second collided with a vehicle of mass 1,200 kilograms moving in the same direction at a speed of 5 meters per second. The two vehicles locked together on impact. Calculate the velocity of the two vehicles immediately after impact. So pause the video now, then unpause the video when you want to go through your answer. So we've got to use the conservation of momentum. So it's 800 times by 15 plus 1,200 times by 5, the total momentum before. That equals 2,000 times by v, because they're now locked together. So it's 18,000 equals 2,000 v. V equals 18,000 over 2,000, and it's 9 meters per second. Let's now have a look at some exam style questions regarding this topic. Engineers are testing the emergency acceleration performance of a self-driving vehicle on a flat road. They record the time taken for the vehicles to accelerate from rest to a set speed of 12 meters per second under different loading conditions. All other driving conditions are held constant. The car's driving force is measured at 2,600 newtons, and here are the results. Using Newton's second law and the data, assess whether the driving force applied to the car remains approximately constant across 3 tests. The engineers suggest that vehicles with the largest mass have the most inertia. Use the concept of Newton's first law to evaluate this claim and explain how it relates to the vehicle's acceleration. Then, if the vehicle encountered a gentle uphill slope during the final trial, discuss how this would affect your interpretation of the results. What assumptions in your previous analysis would no longer be valid. So pause the video now, then unpause the video when you want to go through your answer. Okay. In this first one, we know acceleration is the change in velocity over the change in time. So you can work out the acceleration for each of the different vehicle masses. So it's going to be for 800 kilograms to be 3.25 meters per second, for 1,000 kilograms 2.60 meters per second, and for 1,200 kilograms A is equal to 2.16 meters per second squared. We know F equals ma, so for 800 it's going to be 2,600 newtons, for 1,000 it's 2,600 newtons, and for 1,200 kilograms it's 2,592 newtons. So all the forces, you can conclude, are approximately consistent across the trials. In the second question, Newton's first law indicates objects resist change in its motion, which is inertia. Inertia depends on the mass. The larger the mass, the more the resistance to acceleration. So the higher mass gives you the lower acceleration for the same force, as seen in the data. Now this claim is therefore valid because the 1,200 kilogram vehicle has the greatest inertia, so accelerates the slowest. Now, the slope introduces an additional resisting force, a component of the weight, so reducing the net forward force. Our assumption of a flat road is therefore invalid, so your Newton's second law calculation is no longer accurate without including this extra value of the force. So our interpretation that this force is constant is flawed, as the apparent force would actually be seen to be smaller than the actual engine output would suggest. The next question says, an engineering team is testing a jet-powered flight suit on a tethered launch platform. The suit has two downward-facing jets, each providing an adjustable thrust. During one test, the pilot remained stationary, hovering just above the platform. The engineers collect the following data during the stationary hover. Combined jet thrust 1,450 newtons, mass of the pilot and equipment 145 kilograms, and the contact force on the tether scale is 0 newtons. In a second test, the pilot tilts forward and begins accelerating horizontally at 1.2 meters per second squared, while still being tethered vertically. Explain how Newton's third law applies during the vertical hover, identify the relevant action-reaction force pair, and evaluate how this relates to the 0 reading on the tether scale. During the forward acceleration, describe and explain the horizontal interaction between the pilot and the surrounding air. Then engineers suggest increasing thrust to improve horizontal acceleration. Evaluate the suggestion using Newton's laws and discuss what unintended effects might arise if vertical thrust also increases. So pause the video now, then unpause the video when you want to go through your answer. So in this first one, the jet thrust acts downwards on the air. Air exerts an equal and opposite force upwards on the suit, Newton's third law. These forces are equal in magnitude, opposite in direction, and act on different bodies. The resultant upward force balances the weight, the net force is 0 and it hovers. There is no contact force at the ground, so the tether scale would read 0. Secondly, the jet tilts to direct thrust backwards against the air. Air is pushed backwards, so you get a reaction force pushing the pilot forward. So they've got a Newton's third law pair. The action equals the force on the air, and the reaction is the equal and opposite force on the pilot. So a horizontal acceleration arises from this particular force. Finally, increasing the rearward thrust will give you a greater forward acceleration because you get a greater reaction force via Newton's third law. But if the vertical thrust also increases, our net vertical force becomes upwards. This might make the pilot ascend unintentionally, so engineers must control the direction and magnitude of the thrust accurately to avoid instability for the pilot. A snowboarder is practicing a high-speed landing onto a padded mat designed to reduce injury. The snowboarder has a combined mass of 72 kilograms. They descend the slope and reach a speed of 9.5 meters per second just before landing. Upon impact with the mat, the snowboarder comes to rest in 0.18 seconds. The mat is designed to reduce the maximum impact force experienced by the snowboarder. Engineers are reviewing whether the mat is working as intended by comparing theoretical and measured impact forces. So calculate the change in momentum of the snowboarder during impact. Then calculate the average force exerted on them by the mat. In a different trial with a firmer mat, the stopping time is halved. Estimate the new average force act on the snowboarder and discuss the effect this would have on the injury risk. Evaluate how well using stopping time and average force describes the real experience of impact. Consider any assumptions or simplifications in your calculations. So pause the video now, then unpause the video when you want to go through your answer. Okay, so we know the initial momentum is mass times by velocity is 72 times by 9.5, so it's 684 kilogram meters per second. Our final momentum is 0 because it's at rest, so our impulse is the change in momentum and is 684 newton seconds. Force is impulse over time, 684 over 0.18, 3,800 newtons. In our second question, the stopping time is halved, so our new time is 0.09 seconds. The new average force is therefore 684 over 0.09, 7,600 newtons. The greater force gives you a greater injury risk, so therefore the mat is less effective at reducing the peak force. Finally, we're assuming constant force during impact. Real collisions often have a non-uniform force. The peak force may be higher than the average force calculated, so the model does not account for the energy absorbed by the deformation of the board or by body mechanics. Our next question says, at a skate park, two riders test a new trick involving a collision between their boards. Rider A on a 2.5 kilogram board moves at 4 meters per second towards Rider B. Rider B on a 3.5 kilogram board is initially stationary. After the boards collide, both boards move off in the same direction at 2.3 meters per second. An instructor reviewing the video wants to know how efficient the collision was in terms of kinetic energy transfer. Determine whether the total momentum was conserved during the collision. Calculate the total kinetic energy before and after the collision. Determine whether the collision was elastic or inelastic. And then evaluate how the result of this collision would differ if the boards rebounded from one another instead of sticking together. So consider how momentum and kinetic energy would be affected. So pause the video now, then unpause the video when you want to go through your answer. In the first one, what's the total momentum beforehand? 2.5 times by 4 plus 3.5 times by 0. So it's 10 kilogram meters per second. Our final momentum, we've now added the masses, so it's 2.5 plus 3.5 times 2.3. It's 13.8 kilogram meters per second. So the momentum is not conserved. There's a contradiction there. So the data implies there must be an external force or an error in the observation. So it can't be an isolated system. We know that the kinetic energy is a half mv squared. So initially it's a half times by 2.5 times by 4 squared. We don't have to consider the other board because it's stationary. So it's 20 joules. The final kinetic energy is a half times by 6, the mass of the two boards together, times by 2.3 squared, 15.8 joules. So the energy loss is 4.13 joules. So kinetic energy is not the same and the collision is not elastic. So the loss is likely converted to sound, thermal energy or deformation of the skateboard. Now in the rebounds, the boards will be moving in opposite directions after impact, so their relative speeds will be maintained. Now if the kinetic energy is conserved, you would have an elastic collision and no energy loss. But in reality, rebounds often result in a greater force and possibly higher kinetic energy due to deformation. So it's going to be partially inelastic in this real world scenario. The next question says, in a physics demonstration using an air hockey table, two identical pucks, each of mass 0.20 kilograms, collide. Puck A travels at 2 meters per second due east. Puck B is stationary. After the collision, Puck A moves off at 1.2 meters per second, 30 degrees north of east. Puck B moves off at an unknown speed in a direction 45 degrees south of east. The collision takes place on a frictionless surface. By resolving momentum into components, determine the speed of Puck B after the collision. Determine whether the collision was elastic or inelastic, and evaluate whether your analysis would still be valid if the surface was not frictionless. So pause the video now, then unpause the video when you want to go through your answer. Okay, so we know in the x direction before, in the horizontal, it's going to be mass times by velocity, 0.2 times by 2 equals 0.40 kilogram meters per second. There's going to be no momentum in the y direction as there's no vertical movement. Now the x direction afterwards for A is going to be 0.2 times by 1.2 times by cos 30. So it's going to be 0.20 kilogram meters per second. In the y direction for A afterwards, it's going to be 0.2 times by 1.2 sine 30. So it's going to be 0.12 kilogram meters per second. We therefore know for momentum to be conserved, in the x direction for B, it must be 0.20 v cos 45, and in the y direction it must be minus 0.20 v sine 45 to get them conserved. So therefore in the x direction, we know it's 0.4 before equals 0.20 plus 0.20 v cos 45. So when we work it through, we get v cos 45 to be 0.96, and in the y direction, beforehand was 0, afterwards it's 0.12 minus 0.20 v cos 45. So in this case, v sine 45 is equal to 0.60. So if we want to take that one, we can say v is equal to 0.60 over sine 45, so it's 0.85 meters per second. We know kinetic energy is a half mv squared. Initially, it's a half times by 0.2 times by 2 squared, 0.40. Afterwards, we know that vertically, we're going to work it through into the two different pucks, I should say. So it's a half times by 0.20 times by 1.2 squared, plus a half times by 0.2 times by 0.85, I'll answer the previous question, squared. So equals 0.072, the kinetic energy is not the same, the collision is not elastic. Now friction would introduce external forces into the situation. Momentum is not conserved, and our analysis assumes an isolated system, so if the friction exists, the results will be no longer valid. The next question says, the mass of a car is 1,850 kilograms. Some people sit in the car. The car accelerates at 0.230 meters per second squared, when the resultant force on the car is 460 newtons. Calculate the total mass of the people in the car. So pause the video now, then unpause the video when you want to go through your answer. So we know F equals ma. So it's 460 equals mass times by 0.2. So the mass total is 1,850, the car, plus the mass of the people. That's got to equal in total, therefore, 2,000 kilograms. So the mass of the people must be 150 kilograms. The next question says, state in words the relationship between the force acting on a body and the momentum of a body. A container rests on a top-pan balance which measures the mass in kilograms. A funnel above the container holds some sand. The sand falls at a constant rate of 0.300 kilograms per second into the container, having fallen through an average vertical height of 1.60 meters. Show that the velocity of the sand as it lands in the container is 5.6 meters per second. Calculate the magnitude of the momentum of the sand that lands in the container in each second. Then the mass of the container is 0.650 kilograms. Show that the reading of the balance 10 seconds after the sand starts landing continuously in the container will be 3.82 kilograms. You may assume that the sand comes to rest without rebounding when it lands in the container. So pause the video now, then unpause the video when you want to go through your answer. Okay, we know the force is equal to the rate of change of the momentum. In this question, we know that we're starting off as a potential energy store because it's high up, so it's mgh. It turns into a kinetic energy store, half mv squared. We can equate them. So v equals the square root of 2gh. So it's the square root of 2 times by 9.81 times by 1.6. So therefore it's 5.60 meters per second. Our momentum every second is therefore going to be the mass, which is 0.30 in 1 second, times by the which is the velocity, okay, which is therefore going to be 5.6, which is 1.68 newtons per second. Now the mass of the sand falling in 10 seconds is therefore going to be 0.3 times by 10, so it's 3 kilograms. So therefore our force is our momentum arriving each second, which is 1.68. So the equivalent mass reading is going to be 9.81 over 1.68. So the sand hitting the container is going to produce an equivalent mass reading on the scale of 0.17 kilograms. We know that therefore that the container is going to be 0.65, and we know that the mass of the sand itself is 3 kilograms, so the overall value will be 3.82 kilograms. A child is standing on a skateboard and both are stationary. The child throws a ball forward at a high velocity and the child and the skateboard move backwards at a lower velocity. Explain in terms of momentum why the child and the skateboard move backwards at a lower velocity. So pause the video now, then unpause the video when you want to go through your answer. In this answer, the initial momentum is 0. Now, due to the conservation of momentum, the total momentum before the ball is thrown is equal to the total momentum after the ball is thrown. So this means that the final total momentum is 0. So the momentum of the child and the skateboard must be equal to the momentum of the ball. The momentum of the child and the skateboard must be in the opposite direction to the momentum of the ball to equal 0. So as the mass of the child and skateboard is greater, the velocity of the child and the skateboard must therefore be lower to equal that value out. Curling is a sport played on ice. The players slide stones made of granite along the ice. Each stone has a mass of 19.1 kilograms. A player slides a stone at a velocity of 1.70 meters per second towards the stationary stone as shown before. The stones collide, and after the collision both stones move off as shown. Show that the velocity v is about 1.3 meters per second, and deduce whether the collision is elastic, and your answer should include a calculation. So pause the video now, then unpause the video when you want to go through your answer. So in this first one, we know that momentum beforehand, when it's moving horizontally, is equal to mv is 19.1 times by 0.87. So it's 16.6 kilogram meters per second. Now we know that the total vertical momentum beforehand was 0 because there was no vertical motion. So the vertical momentum for the upper stone and the lower stone must in fact equal each other out. We can work out the momentum vertically for the upper stone by doing 16.6 times by sine 50 because we know it's moving off in that particular value through. So we get it to be 12.7 kilogram meters per second. That must be equaled out by the lower stone because they've got to add together to equal 0. So they're going to be the same magnitude, just opposite signs. So we know 12.7 equals the mass of it, 19.1, times by v sine 30. So therefore v is going to be 12.7 over this value to work it through, because sine 30 is going to be equal to 0.5. So you can work it out to be 1.33 meters per second. Now the next question, we know kinetic energy is a half mv squared. So beforehand, it's a half times by 19.1 times by 1.7 squared, which is 27.6 joules. Now afterwards, it's going to be a half times by 19.1 times by 0.87 squared plus a half times by 19.1 times by 1.33 squared, because we've now got the two stones moving. So afterwards, in total, it's going to be 24.1 joules afterwards. So initially, it was about 28, afterwards it's about 24, so kinetic energy is not the same, the collision is not elastic. So that brings an end to our revision session today. If we've been successful and we've learned in today's revision session, we should be able to answer A-level physics examination style questions, assess our understanding on A-level physics, and then understand what topics we need to improve upon for A-level physics. So thank you so much for watching this revision session for AQA A-Level Physics on the topic of mechanics, on Newton's laws and momentum. Thank you so much for watching and have a lovely day. Hello and welcome to this revision session for AQA Paper 1 in the topic of mechanics, looking at the concept of motion in projectiles. So if we've been successful and we've learned in today's revision session, we should be able to answer A-level physics examination style questions, assess our understanding on A-level physics, understand what topics we need to improve upon for AQA A-level physics. So how should you prepare for this revision session? When you're completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and in this left hand side section write down your working out and answers to the questions in the revision session. When you're doing this, make sure you write your answers in full sentences and show your full working out. Whilst on the right hand side, write down any bits of information which you find useful or any hints and tips on answering questions from this revision session. After the end of the revision session, write up these notes into a revision sheet for you to use independently. So how should you be revising for AQA A-Level Physics? So the first step is to learn the key facts. Use revision guides, class workbooks, prep notes and the textbooks to learn the key ideas of the course. You may wish to make mind maps or to write out the notes yourself. Secondly, test yourself. Use things like Caboodle, Seneca, knowledge checkers to quickly test your own knowledge, and you may wish to do this from your own cue cards. Third step is to use exam practice books, homework books, supervised study books, additional workbooks to answer examination questions and mark your own work. So you may wish to download your own exam past papers to do this. So the three steps of learn the key facts, testing yourself and practicing exam style questions are how you should be revising for your AQA A-Level Physics exams. So in terms of revision, in this session we're going to be looking at two types of questions. The first are the general check questions, the basic questions designed to probe your understanding of the key concepts of the topic. We'll then be looking at assessment point questions, past paper examination questions, which will mimic the types of questions found in public examinations. So let's start off with our general check questions. So consider an object falling after 0 seconds, 1 second, 2 seconds, 3 seconds and 4 seconds. If our object starts at rest, what is the acceleration at each time? So pause the video now, then unpause the video when you want to go through your answer. Well, at 0 seconds, it's 9.81 meters per second squared. It's the same at 1 second. It's the same at 2 seconds. It's the same at 3 seconds. And it's the same at 4 seconds. Now, what's the object's velocity going to be at 0, 1, 2, 3, and 4 seconds? So pause the video now, then unpause the video when you want to go through your answer. Well, at 0 seconds, it's 0 meters per second. At 1 second, it's 9.81 meters per second. At 2 seconds, it's 19.62 meters per second. At 3 seconds, it's 29.43 meters per second. And at 4 seconds, it's 39.24 meters per second. What is the displacement at each time of this object? So pause the video now, then unpause the video when you want to go through your answer. Well, at 0 seconds, it's no meters. At 1 second, it's a half gt squared, so it's a half times by 9.81 times 1 squared, so it's 4.91 meters. At 2 seconds, it's 19.62 meters. At 3 seconds, it's 44.15 meters. At 4 seconds, it's 78.4 meters. If a heavy object and a light object are dropped from the same height in a vacuum, which will reach the ground first and why? So pause the video now, then unpause the video when you want to go through your answer. Now both will reach the ground at the same time. In a vacuum, there is no air resistance, so all objects fall with the same acceleration due to gravity, regardless of mass. A ball is thrown upwards. At the highest point in its path, what is the acceleration of the ball? So pause the video now, then unpause the video when you want to go through your answer. The acceleration at the highest point is still 9.81 meters per second downwards. Gravity will continuously act on the ball even when it momentarily stops at the top of its trajectory. As an object in freefall speeds up, does its acceleration increase, decrease, or stay the same? So pause the video now, then unpause the video when you want to go through your answer. The acceleration stays the same. For objects in freefall near the Earth's surface, ignoring air resistance, the acceleration due to gravity will always be 9.81 meters per second squared. If an object is dropped from a height, does it reach terminal velocity immediately, and why? So pause the video now, then unpause the video when you want to go through your answer. No, it takes time and distance for an object to reach terminal velocity, as the air resistance needs to build up to balance the force of gravity. An object in true freefall, like in a vacuum, will never actually reach terminal velocity as there's no air resistance. A stone is thrown downwards from a height. Is its acceleration greater than, less than, or equal to 9.81 meters per second squared, and why? So pause the video now, then unpause the video when you want to go through your answer. The acceleration is equal to 9.81 meters per second squared. Regardless of the initial velocity or direction of the motion, the only acceleration acting on the stone is due to gravity, which is 9.81 meters per second downwards. True or false, the velocity of an object in freefall increases as it falls, so its acceleration must also be increasing. Pause the video now, then unpause the video when you want to go through your answer. Whilst the velocity increases as the object falls, the acceleration remains constant at 9.81 meters per second squared. Acceleration due to gravity does not change with increasing speed. If a feather and a hammer are dropped at the same time from the same height on Earth with air resistance present, which one hits the ground first? So pause the video now, then unpause the video when you want to go through your answer. The hammer will hit the ground first due to air resistance. In the presence of air, lighter and less aerodynamic objects like feathers experience more air resistance relative to their weight, slowing their fall. If an object falls with air resistance, how is its motion different compared to falling under free fall? So pause the video now, then unpause the video when you want to go through your answer. With air resistance, the time taken to fall would increase, and the final velocity and acceleration will be lower for the object. For projectile motion, is the velocity ever zero? So pause the video now, then unpause the video when you want to go through your answer. No, the velocity is never zero in projectile motion. Even at the peak of the motion, when the vertical velocity of the component is zero, the horizontal velocity component remains non-zero as there's no horizontal acceleration. For projectile motion, when is the velocity a minimum? So pause the video now, and then unpause the video when you want to go through your answer. The velocity is a minimum at the peak of the trajectory. For projectile motion, when is the velocity a maximum? So pause the video now, then unpause the video when you want to go through your answer. The velocity is at a maximum at the instant the projectile is launched and just before it strikes the ground, ignoring air resistance. Now for projectile motion, can the velocity ever be the same as the initial velocity at a time other than t equals 0? So pause the video now, then unpause the video when you want to go through your answer. No, the velocity vector, including direction, cannot be the same as the initial velocity at any time other than t equals 0. Whilst the magnitude of the speed might match, the direction changes due to the influence of gravity. For projectile motion, can the speed ever be the same as the initial speed at a time other than t equals 0? So pause the video now, then unpause the video when you want to go through your answer. Yes, the speed can be the same as the initial speed at some point during the motion. This occurs when the projectile returns to the same vertical height as the launch point on its downwards trajectory. For projectile motion, is the acceleration ever zero? So pause the video now, then unpause the video when you want to go through your answer. No, the acceleration is never zero in projectile motion. The projectile will always experience a constant acceleration due to gravity acting downwards. For projectile motion, is the acceleration ever in the same direction as the component of velocity? When you want to go through the answer, pause the video, then unpause the video. So So, yes, the acceleration is in the same direction as the vertical component of velocity when the projectile is moving downwards. This is because both the vertical velocity and the acceleration point downwards. For projectile motion, is the acceleration ever opposite in direction to a component of velocity? So pause the video now, then unpause the video when you want to go through your answer. Yes, the acceleration is in opposite direction to the vertical component of velocity when a projectile is moving upwards, because the vertical velocity in this case is upwards and the acceleration due to gravity will always be downwards. A professor places two coins on the edge of a table. She then flicks one of the coins horizontally off the table, simultaneously nudging the other one over the edge. Describe the subsequent motion of the two coins, in particular discussing whether they hit the floor at the same time. So pause the video now, then unpause the video when you want to go through your answer. When the professor flicks one coin horizontally while the other falls straight down, both coins experience the same downward acceleration due to gravity. The horizontal motion of the flick coin does not affect the time taken to hit the ground, as the vertical motion is always independent of the horizontal motion. Both coins will hit the floor at the same time. The horizontally flicked coin, however, lands farther away from the table due to its horizontal velocity. A car is on a road with a set of traffic lights ahead. The car starts from rest. The car then accelerates at a constant rate of 3 meters per second for 8 seconds. Calculate the velocity of the car after 8 seconds. Then the car then decelerates at a constant rate of 4 meters per second squared and stops at the traffic lights. Calculate the distance travelled by the car whilst it is decelerating. So pause the video now, then unpause the video when you want to go through your answer. Okay, we know that we can use our equations of motion. V equals u plus at, v equals 0 plus 3 times 8, v equals 24 meters per second. We can, in the second one, use v squared equals u squared plus 2as. So s equals v squared minus u squared over 2a. So it's going to be minus 576 over minus 8, so it's 72 meters. Let's now have a look at some exam style questions. In a publicity stunt for a science expo, a rocket-powered shopper trolley is fired along a flat car park. A brick wall stands 85 meters from the starting line. The trolley starts from rest and accelerates uniformly, reaches a maximum speed of 22 meters per second exactly 6 seconds after the launch. The boost is cut off immediately after 6 seconds, after which the trolley continues at a constant speed. To protect the equipment inside the trolley, an automatic braking system is designed to bring the trolley to a stop safely if triggered. Determine the total distance the trolley travels in the first 6 seconds. Then determine how far it is away from the wall when the boost is cut off. Assuming the braking system is triggered at exactly 6 seconds, and the trolley can decelerate uniformly at a maximum rate of minus 4 meters per second squared, determine whether the trolley would stop before hitting the wall. The engineers consider delaying the activation of the brakes by 2 seconds to avoid false triggers. Would this change result in a collision? So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we can say A equals V minus U over T. So it's 22 minus 0 over 6. So it's 3.67 meters per second squared. Then we say S equals UT plus a half AT squared. Work it all through and we get 66.1 meters. So therefore it's 18.9, 85 minus 66.1 meters from the wall at the cutoff. In the second question, we use v squared equals u squared plus 2as. So 0 equals 22 squared plus 2 times by minus 4 times by s. So therefore s equals 60.5 meters. Now we compare this stopping distance, 60.5 meters, to the remaining distance, 18.9 meters. So therefore it's not enough room to stop, so the trolley would hit the wall. Now in 2 seconds at 22 meters per second, the trolley will travel 44 meters. As we mentioned before, the remaining distance to the wall is going to be 18.9 meters. So that's a difference of 25.1 meters. So the trolley will crash into the wall before the brakes would even activate in this scenario. Engineers are testing a hydraulic launch system on a new vertical roller coaster. The car starts from rest at the bottom of the track. It is launched up a straight vertical section 40.0 meters tall. The launch acceleration lasts for 5 seconds and the car reaches a speed of 32 meters per second at the end of the launch. There is no additional propulsion after launch. The car ascends vertically under gravity alone once the launch ends. A platform is located at the top of the vertical section. The engineers want to know whether the the car will reach it. Determine whether the car reaches the top of the vertical section using the information from the launch. If the car does not reach the platform, calculate the total time from launch start to the moment it reaches maximum height. During the 5-second launch, the car and the passenger gain 240 kilojoules of kinetic energy. The launch system consumes 480 kilojoules of energy in total. Calculate the average power output of the launch system during the 5 seconds and determine its efficiency. So pause the video now, then unpause the video when you want to go through your answer. In this first one, we can say S equals v squared minus u squared over 2a. So when we work that through, we get 52.2 meters. So therefore the car rises 52.2 meters. The platform was only 40 meters tall, so it will reach the platform. In the second question, v equals u plus at. Now we then got to use, say, 32 plus minus 9.81 times by t, because we go in the opposite direction. So therefore t is equal to 3.26 seconds. So the time from the powered launch is 5 seconds, so therefore the total time is 8.26 seconds. Power is going to be the work done over the time, 480,000 because kilojoules into joules, over 5 is 96,000 watts. The useful output is going to be 240,000 joules. The total input of energy is 480,000, so therefore our efficiency is 50% or 0.50. In a penalty shootout at a football event, a player attempts a trick shot from the penalty spot 11 metres from the goal line. They kick the ball at a speed of 18 metres per second at an angle of 25 degrees above the horizontal. The ball must pass over a defender who jumps vertically and reaches a maximum height of 2.20 metres directly in the ball's path. The defender is positioned 6 metres in front of the kicker. The crossbar of the goal is 2.44 metres above the ground. Determine whether the ball will pass over the defender. Assuming the ball clears the defender, determine whether it will go over the crossbar or go into the goal. The player says, if I'd used more power, it had just gone over the bar. Evaluate this claim using physics principles. Would increasing the initial speed necessarily improve the outcome? So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, our horizontal speed is going to be 18 cos 25 when we consider our angle, so 16.3 meters per second. So therefore our time to reach the defender is 6 over 16.3, so it's going to be 0.368 seconds. The vertical speed is 18 sine 25, so it's 7.6 meters per second. The vertical position at the time, we can then work it out to be vt minus a half gt squared, because we're getting gravity pulling it down. So therefore 7.6 times by 0.368 minus a half times by 9.81 times by 0.368 squared. So it's 2.16 meters. So the ball does not clear the defender, who is 2.2 meters in height. The next question, we know the time to the goal line is going to be 11 meters over 16.3, which is the velocity. So therefore it works it through, and then we can get it out to be 0.675 seconds. We can work out the vertical height as going to be vt minus a half gt squared. So you work it through to be 2.16 meters. So compare that to the crossbar. Okay, therefore the ball will go over the crossbar if it cleared the defender. Now the next question says, increasing the speed will therefore increase both the vertical and horizontal components of the velocity. The higher the vertical speed, the higher the trajectory. So the ball is more likely to clear the defender at the goal, but also increases the time and the range, so it could either overshoot or hit the bar depending on the angle. So it's not going to be a guaranteed success. The next question says, during a beach volleyball match, a player dives to save a ball. They jump from a height of 1.5 meters above the sand, launching horizontally at a speed of 5.2 meters per second. The ball is falling vertically towards the sand 3 meters in front of the player at the moment they jump. To make the save, the player's hand must be level with the ball when it is 0.2 meters above the sand. Determine whether the player reaches the ball before it drops below 0.20 meters. The coach suggests that the player could improve their dive by jumping at a slight upward angle instead. Explain whether this change could realistically help and what physics principles affect that outcome. Then, assuming the player must land safely, calculate the vertical velocity component just before landing. Hence, calculate the kinetic energy associated with their vertical motion and impact, and discuss the implications for an injury risk. So pause the video now, then unpause the video when you want to go through your answer. In this first one, the time to reach the ball horizontally is going to be equal to 3, the distance, over the speed, 5.2, 0.577 seconds. Now our displacement is going to be ut minus a half gt squared because it's coming upwards, so therefore it's going to be negative acceleration due to gravity. So we work it through to be minus 0.13 meters. So this tells us that the ball will hit the ground before the player arrives. In the next question, jumping upwards increases the time in the air. Now the longer the air time allows greater horizontal distance to be covered, but the upward vertical velocity reduces the horizontal component unless the total speed is increased. So to help, the player must maintain or increase the total speed or adjust their launch angle. We know that the kinetic energy will turn into gravitational potential energy, so a half mv squared equals mgh. So v equals a square root of 2gh, so you pop all the values in and you get 5.42 meters per second. So our kinetic energy is a half times by 1 times by 5.2 is 5.42 squared, which is 14.7 joules for every kilogram. So this tells us that the higher the vertical kinetic energy, the greater the impact force. So there's a potential for injury if the person is not cushioned. A performance car and a superbike are tested on a straight, level, 200-meter track from rest. Both vehicles accelerate uniformly from rest. The car reaches a speed of 28.0 meters per second in 6 seconds. The motorbike reaches a speed of 32 meters per second in 5 seconds. The car has a mass of 1,100 kilograms and the motorbike has a mass of 250 kilograms. The engines in both vehicles convert fuel energy into kinetic energy, but not all the fuel energy is transferred usefully. Use the information provided to determine which vehicle will travel farther after 5 seconds. Estimate the total work done on each vehicle during acceleration and hence determine which one has the most efficient energy transfer if each engine used 600 kilojoules of chemical energy during that test. Assume that the motorbike reaches 32.0 meters per second in exactly 5 seconds. Estimate the average power output of the engine during this time and comment on how this compares with the car's power output. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question we can say S equals ut plus a half at squared. So for the car it's going to be 0 plus 0.5 times by 28 over 6 times by 5 squared, which is 58.4 meters. For the motorbike it's 0 plus a half times by 32 over 5 times by 5 squared, which is 80 meters. So the motorbike will travel further in 5 seconds. Next, we know that the kinetic energy of the car is a half times by 1,100 times by 28 squared, which is 431,200 joules. For the motorbike, it's a half times by 250 times by 32 squared, 128,000 joules. So our efficiency we do for our car is going to be useful energy out over total energy in, which is 71.9%, and for the motorbike, it is 21.3%. So despite being faster, the motorbike's engine is less efficient. Now, in this next one, our power output is the work done over the time taken. So it's 128,000 over 5. So it's 25.6 kilowatts. Now, the car's power is 431,200 joules over the 6 seconds, which is 71.9 kilowatts. So the car engine delivers more power despite slower top speed. So there's a greater work being done and more force being exerted over a particular time. The next question says, a mountain rescue team pulls a supply sledge up a snow-covered incline to reach a stranded hiker. The sledge and its contents have a mass of 150 kilograms, and the team pulls it up a 25-degree incline with a constant force of 1,200 newtons using a rope aligned 15 degrees to the slope. The rope remains taut and the sledge moves 15 meters along the slope with a constant speed. Some of the work done is lost as thermal energy due to the friction between the sledge and the snow. Determine the work done by the rescue team in pulling the sledge up the slope. Calculate the energy transfer to other stores during the pull. The team claims that our pulling force is almost perfectly efficient. Evaluate this claim using your previous answers. Discuss the assumptions made in your calculation and how they affect the reliability of this statement. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first question, work done is force times by displacement times by cos theta, 1,200 times by 15 times by cos 15, 17,388 joules. Our vertical height gained is 15 sine 25. So it's 6.34 meters. So our potential energy, MGH, is 150 times by 9.81 times by 6.34, 9,330 joules. Now, other energy, so the work done, okay, is going to be the gravitational potential increase. Okay, so it's going to be the work done minus the gravitational potential energy increase, which is 17,388 minus 9,330. So the work done by the other stores is 8,060 joules. So this is most likely going to be going to the thermal store due to friction. Now, efficiency is useful energy output over total energy input. So it's 9,330 over 17,388, which is 53.7%. So it's not almost perfect, and it assumes that no energy is stored as kinetic, all friction converts to thermal, and then the force is constant and our angles are measured accurately. Now, the reliability depends on these assumptions, but you have real world losses, such as things like air resistance, which could reduce efficiency even further. The next question says, the crossbar challenge is a football contest where competitors try and hit the crossbar of a goal by kicking a football from the penalty spot. The horizontal distance between the penalty spot and the crossbar is 11 metres. One competitor kicks a football with an initial velocity of 17 metres per second at an angle of 24 degrees to the horizontal. The football hits the crossbar. The effects of air resistance can be ignored. Calculate the horizontal component, the initial velocity of the football. Calculate the vertical component, the initial velocity of the football. Show that the time taken for the football to travel from the penalty spot to the crossbar is 0.71 seconds. The football is at a maximum height in its trajectory when it hits the crossbar. Calculate the height above the ground at which the football hits the crossbar. The next time the competitor tries the challenge, they kick the football at the same angle with an initial speed less than 17 meters per second. State whether the football hits the crossbar, passes over the crossbar, or passes under the crossbar. Justify your answer. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, horizontal component is going to be 17 cos 24, so it's 15.5 meters per second. Vertical, 17 sine 24, 6.91 meters per second. The time is the speed over the velocity, and we're doing the horizontal one here, so it's 11 over 15.5, 0.71 seconds. The height, we can use S equals ut plus a half at squared. Remember, it's minus 9.81 as we're going upwards and gravity is downwards, so you get 2.4 meters. Now, in the last question, the football will pass under the bar because there's a smaller vertical velocity, so it will not reach the same height. Figure 7 shows a robotic helicopter that is used on Mars. Figure 9 shows a simplified side view of the helicopter moving vertically upwards with a speed of 0.55 meters per second. At the instant shown, the helicopter is at a height h and the blades stop rotating. The gravitational field strength of Mars is 3.72 newtons per kilogram. The weight of the helicopter is the only force acting upon it when the blades stop rotating. The drag forces on the helicopter are negligible as it rises to a maximum height and then falls back to the surface. Calculate the time taken for the helicopter to reach its maximum height when the instant the blade stops rotating. When the helicopter makes contact with the surface, it has a velocity of 2.2 meters per second. Calculate h. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we can say v equals u plus at. So t equals v minus u over a. You pop in all the values and you get 0.15 seconds. Secondly, we can use v squared equals u squared plus 2as. So we can say 2.2 squared equals 0 squared plus 2 times 3 times 3.7.2 times by s, so s is 0.61 meters. The next question says, in 2016, the European Space Agency sent a probe to Mars. As the probe approached the surface of Mars with a vertical component of 460 meters per second for the velocity, a parachute was opened to reduce the speed of the probe. Once the vertical velocity of the probe had reduced to 75 meters per second, the parachute was removed and the thrusters were switched on. Due to an error, the thrusters were switched off too soon, leaving the probe to freefall to the surface of Mars. The parachute was used to decrease to a height of 9.7 kilometers. The probe was in freefall from a height of 3.7 kilometers, reaching the surface of Mars with a velocity of 150 meters per second. Explain whether the term freefall is correct in this context. Your answer should include a calculation. The gravitational field strength on Mars is 3.8 newtons per kilogram. So, pause the video now, then unpause the video when you want to go through your answer. Right, in your answer, freefall means that the weight is the only force acting on the probe. but there will also be resistive forces acting on the probe. Now we can have to work out the acceleration due to the object and work out if it's the same as the free fall. So v squared equals u squared plus 2as. Use information from the question and the diagram to work it out to be 2.4 meters per second squared. The acceleration of the free fall on Mars is the gravitational field strength, so it's 3.8 meters per second squared. 2.4 is lower than 3.8, so it was not in free fall. A trebuchet is a medieval catapult designed to project a rock over large distances. A simplified diagram of a trebuchet is shown. The rock is held in a sling. When the peg is removed, the counterweight falls and the rock is projected through the air. A student assumes that all the gravitational potential energy transferred from the counterweight is transferred to the kinetic energy of the rock. Give 2 reasons why this is not correct. The rock was projected with a velocity of 41.5 meters per second at an angle of 30 degrees to the horizontal. The diagram shows the flight of the rock after it has left the trebuchet. The rock rises to a maximum height and then falls back to the same height as its release height. Calculate the horizontal distance travelled by the rock in this time. The mass of the counterweight was reduced. The trebuchet was then used to project the rock again. Explain why the horizontal distance travelled by the rock decreases. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, the beam or the sling and the counterweight gain kinetic energy and gain gravitational potential energy. There is work done against friction, so some energy will be transferred to the surroundings. We know that the initial vertical velocity is going to be 41.5 times sine 30, so it's 20.8 meters per second. The horizontal velocity is 41.5 cos 30, or 35.9 meters per second. We can use v equals u plus at, and we know that at the maximum height, the velocity is going to be 0. So 0 equals 20.8 minus 9.81 times by t. So t equals 2.12. So the time to the maximum height is 2.12 seconds. So our distance to that is the speed times the distance it will travel overall is going to be the horizontal velocity, 35.9, times by twice the distance time, so twice the time to the maximum height, because that is halfway through the journey. So it's 35.9 times by 2 times by 2.12, 152 meters. Now the counterweight transfers less gravitational potential energy, so the transfer of kinetic energy to the rock is reduced. So when released, the rock has a smaller vertical component of velocity, so the time of flight will be reduced and the horizontal component of velocity will be smaller. The next question says, a tennis player strikes a ball at a height of 2.5 meters above the ground. The ball leaves the racket, traveling horizontally at 24 meters per second. It travels through the air and hits the ground at point X on the other side of the net. The effects of air resistance can be ignored. The ball takes 0.50 seconds to travel to the net. Calculate the height of the ball above the ground at this time, and then calculate the velocity as it hits the ground at X. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we can use the equations of motion, s equals ut plus a half at squared. Remember, it's going to be a negative acceleration as it's going upwards and gravity acts downwards. So it's going to be minus 1.225 meters. So the height above the ground is going to be 2.5 minus 1.225, 2.75 meters. Now the velocity at the impact, the vertical velocity, v squared equals u squared plus 2as. We can work it through. Again, remember a is minus 9.81 as it's travelling upwards initially. So you get your vertical velocity to be 7 meters per second. The horizontal velocity stays at a constant because it's a projectile, so it's 24 meters per second. So our resultant velocity is v squared equals the horizontal square plus the vertical squared. So it's 49 plus 576, all square rooted, 25 meters per second. The angle is tan theta is opposite over adjacent, so it's going to be 7 over 24, so you get 16 degrees to the horizontal. Figure 7 shows the robotic helicopter that is used on Mars. The helicopter is powered by a battery. Before each flight, the battery is charged by a solar panel. Figure 8 shows the helicopter hovering at a constant height above the surface of Mars. The rotor blades move a column of atmospheric gas vertically downwards at a velocity of 17.2 meters per second. The diameter of this column is 1.2 meters. The helicopter has a maximum flight of a few minutes due to the limited amount of energy stored in the battery. The battery accounts for about 15% of the helicopter's mass. A student suggests that adding another identical battery that doubles the energy available to the helicopter would double its flight time. Deduce without calculation whether the student's suggestion is correct. So pause the video now, then unpause the video when you want to go through your answer. Right, so it is incorrect because this will increase the weight, or you would say the helicopter's got to have a greater lift to get off the ground. So therefore a greater gravitational potential energy would be needed for the same height, or you could say you would need a greater kinetic energy for the same speed. So ultimately you need more energy. Now the helicopter must also displace more atmospheric gas every second to produce this greater lift force, so the blades will have to spin faster to accommodate this. So ultimately the helicopter will need to do more work every second, so it will be transferring more energy at a greater rate, so you'll need more power. So in fact it would need more power for it to work. So that brings an end to our revision session today. If we've been successful, we can answer A-Level Physics examination style questions. We can assess our understanding on A-Level Physics. And finally, we can understand what topics we need to improve upon for AQA A-Level Physics. So thank you so much for watching this revision session on motion and projectiles, which is a topic in AQA A-Level Physics Paper 1 on mechanics. Thank you so much and have a lovely day. Hello and welcome to this revision session for A-Level Physics on the topic of mechanics on the concept of forces and motion, which is part of AQA Paper 1. So in today's lesson, if we've been successful, we should be able to answer A-Level Physics examination style questions, assess our understanding on A-Level Physics, and understand what topics we need to improve upon for A-Level Physics. So how should you prepare for this revision session? When you're completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side. And in this section, write down your working out and answers to the questions in the revision session. When you're doing this, make sure to write in full sentences and show your full working out. Whilst in the right hand side, write down any bits of information which you find useful, any hints and tips on answering questions from this revision session. After the end of the revision session, write up these notes into a revision sheet for you to use independently. So how should you be revising for AQA A-Level Physics? Well, the first step is to learn the key facts. Use revision guides, student prep books, class workbooks, the textbook to learn the key ideas of the course. Then test yourself. Use things like Caboodle, Seneca, the student knowledge checkers to quickly test your own knowledge. Then finally, use exam practice books, homework books, supervised study books, additional workbooks to answer exam questions and to mark your own work. So learn the key facts, test yourself, and practice exam style questions. So in this revision session, we're going to be looking at forces and moments. So what are the key facts to do with this? Well, a resultant force causes an acceleration. An acceleration is a change of speed or direction. The resultant force must be considered in both horizontal and vertical planes. The resultant force is equivalent to mass times acceleration, which is Newton's second law of motion, F equals ma. We know that a resultant moment will cause an object to rotate. If the moments are balanced on an object, the object will be balanced. A moment is the force times by the perpendicular distance, and a couple is a pair of forces that act in opposite directions, perpendicular to each other with the same magnitude, but will produce a resultant moment. Now, the weight of an object always acts perpendicular down from the centre of mass, which is called the line of action, and the centre of mass is assumed to be at the centre of the object. Now, an object is in equilibrium if there's no resultant moment or resultant force. So let's have a look at some key check questions to do with forces and moments. So our first question says, calculate the magnitude and the direction of the resultant force. So to work out this answer, we say r squared is equal to 2 squared plus 3.1 squared. So therefore r squared is equal to 13.6, so r is equal to 3.7 newtons. We can then say tan theta is opposite over adjacent, so it's going to be 3.1 over 2, which is 1.55, so our angle of theta is 57 degrees. So the resultant displacement is 3.7 newtons at 57 degrees from the horizontal. Calculate the magnitude and the direction of the following resultant force. So we do r squared is equal to 6 squared plus 16 squared, so we get 292. So therefore r is equal to 17.1 newtons. Tan theta is equal to opposite over adjacent, so 6 over 16, which is 0.38. So theta is equal to 21 degrees. So our resultant displacement is 17.1 newtons at 21 degrees from the horizontal. Calculate the magnitude and the direction of the following resultant force. So the first thing we know is that overall in the horizontal, the force is 1 Newton. So therefore r squared is equal to 1 squared plus 1 squared. So r squared is equal to 2. So r is equal to 1.4 newtons. Tan theta is opposite over adjacent, which is 1 over 1. So theta is equal to 45 degrees. So our resultant displacement is 1.4 newtons at an angle of 45 degrees from the horizontal. An aircraft is flying due north with a velocity of 200 meters per second. A side wind of velocity 50 meters per second is blowing due east. What is the aircraft's resultant velocity? So we can say v squared is equal to the vertical velocity squared plus the horizontal velocity squared. So it's 200 squared plus 50 squared, which is 42,500. So therefore v is equal to 206 meters per second. Tan theta is opposite over adjacent, which is 50 over 200, which is 0.25. So theta is therefore equal to 14 degrees. So the aircraft's resultant velocity is 206 meters per second at 14 degrees east of north. Figure 4 shows a meter rule pivoted at its 50 centimeter mark. Two objects of weight 0.70 newtons and W are placed on the ruler as shown to balance it. Assume that the weight of the ruler is negligible. Calculate the size of W. So we know that W is going to be equal to moment over distance, because we know moment is equal to force times by distance. So therefore, what is our moment? So our moment is equal to 0.7 times by 0.32 from the other side of the balance point, and they'll balance out because it's in equilibrium. Then we divide that by 0.14, because we turn centimeters into meters, 1.6 newtons. With the same idea, calculate the force acting on the pivot. Now we know, because it's balanced, it's in equilibrium, that the forces up must equal the forces down. So we can say R is equal to 0.70 plus 1.6, which is therefore equal to 2.3 newtons. Figure 5 shows a model of a loaded section of a bridge made using a uniform wooden beam. R of beam is working it through. Now the wooden beam is 120 centimeters or 1.2 meters long and has a weight of 15 newtons. One end of the beam rests on a support and the other end is fixed to a vertical string. Calculate the vertical force R at the support. So we know that the moments are balanced about the point. So if we take our moments from point A, we can say R times by 1.2 is equal to 15 times by 0.6 plus 13 times by 0.40. Again, we turn our centimeters into meters. Therefore, R is equal to 142 over 1.20. It is equal to 12 newtons. With our same idea, calculate the vertical force T. Once again, we know upwards forces equals downwards forces. So we can say upwards is 12 plus T is equal to the downwards, 13 plus 15. So therefore T will equal 16 newtons. The next question says, explain the following observation. Two people can balance a seesaw even if one is much heavier than the other. Well, the moments can be equal. As the lighter person produces a smaller force, they would need to sit further away from the pivot to generate a moment of equal size. Explain the following observation. It is easy to undo a tight screw using a screwdriver with a large diameter handle. A large diameter handle provides a greater turning effect and hence a greater force on the screw. Old buses and lorries had large steering wheels. Well, old buses and lorries had no power steering, so the large radius of the wheel amplified the turning effect or the moment that was taking place. A windsurfer stands on a windsurf board and holds onto the sail as shown. As the force from the wind increases, the windsurfer leans back further. Explain how leaning back further keeps the windsurfer in equilibrium. Your explanation should make reference to moments. The force from the wind produces an anti-clockwise moment about the point where the sail attaches to the board. So the weight of this windsurfer produces a moment in the opposite direction. So the windsurfer leans back until the moment due to his weight has increased to equal the increased moment of the wind force. Describe the motion of this object. It will accelerate to the right as there's a resultant linear force to the right, and it will spin in a clockwise direction. As you can see, that it's going to cause rotation in a clockwise direction. Describe the motion of this object. It will spin in an anti-clockwise direction. The linear forces cancel through, but the rotational forces will not. Is this a couple, and why? Yes, the forces are equal in size, perpendicular to each other, opposite in direction, and will cause a resultant moment. Is this a couple, and why? No, as the forces are all acting in the same direction. Is this a couple, and why? No, as all the forces are not equal in size. Is this a couple, and why? It's not a couple, as the forces are different magnitudes and they're acting in the same direction. Is this a couple, and why? It is a couple, as the forces of the same magnitude share the same perpendicular plane and are acting in opposite directions. Is this a couple, and why? Yes, it is a couple, as the forces are the same magnitudes, they share the same perpendicular plane and are acting in opposite directions. Is this a couple, and why? It is not a couple, as there's only one force producing a moment on the object. Is this a couple, and why? It is a couple, as the forces are the same magnitudes, share the same perpendicular plane, and are acting in opposite directions. Is this a couple, and why? It is not a couple, as the forces are different magnitudes. Is this a couple, and why? It is not a couple, as the forces are acting in the same direction. Is this a couple, and why? It's not a couple, as the forces have different magnitudes. So let's have a look at some exam style questions to do with forces and moments. A rescue worker is pulling a 25 kilogram sled of equipment up a smooth, icy slope inclined at 18 degrees to the horizontal. She pulls the sled using a rope angled at 30 degrees to the slope, applying a tension of 120 newtons. Assume there is no friction and the sled moves at a constant velocity. Show that the component of the sled's weight parallel to the slope is approximately 75 newtons. Resolve the 120 newton tension into components parallel and perpendicular to the slope, and then use the answers to assess whether the rope is providing sufficient force to keep the sled moving at a constant velocity up the slope. So pause the video now, then unpause the video when you want to go through your answer. Right, we can know that the weight is equal to mass times by gravity, so therefore it's 25 times by 9.81, so it's 245.25 newtons. Now the component down the slope is going to be the vertical component, so we can say it's W sine theta, where the theta is the angle with the horizontal. So therefore W sine 18 is going to equal 245.25 times by sine 18, which is 75.8 newtons. Now to resolve the tension, we can work out horizontally, which is going to be T cos theta, so it's going to be T cos 30, so it's 120 times by 0.866, which is 103.9 newtons. Whilst vertically, which is perpendicular to the slope, is going to be T sine theta, so it's going to be 120 times by sine 30, which is 60 newtons. Now finally, we can work out that the component of the weight down the slope from the first part is 75.8 newtons. The component of the tension up the slope, which you've just worked out, which is going to be along the slope, is 103.9 newtons. This tells us that the tension force is greater than the component of weight. So therefore, if it's moving at a constant velocity, there must be overall no resultant force. So therefore, there must be another force acting down the slope. Now, the motion, as we said, is at constant velocity, so our net force is 0. So therefore, we know the upward tension and the downward weight are going to be balanced, so our sled is going to be in equilibrium. Now, a horizontal maintenance platform of negligible mass is suspended in mid-air by two taut cables attached to a ceiling. Cable A is inclined at 35 degrees to the horizontal and exerts a tension of 620 newtons. Cable B is inclined at 50 degrees to the horizontal and in the opposite direction. A worker and the equipment stand on the platform, exerting a total downward force of 800 newtons at the centre. The system is in vertical equilibrium. Resolve the tension in cable A into horizontal and vertical components. By considering vertical equilibrium, calculate the vertical component of the tension in cable B, hence determine the total tension in cable B. Then assess if the system is in horizontal equilibrium. So pause the video now, then unpause the video when you want to go through your answer. Right, in our first one, horizontally, it's going to be t cos theta, so it's going to be t cos 35. So therefore, it's 620 times by cos 35, which is 355.9 newtons. Vertically, in this case, it's going to be t sine theta, so it's going to be 620 sine 35, so it's 508 newtons. Now we know that the total vertical support needed is going to be 800 newtons because we need our overall vertical force to be 0. So if downwards is 800, upwards must be 800. Now cable A, as we've just worked out, provides 355.9 newtons towards this. So cable B must therefore provide 444.1 newtons vertically. Now we know sine 50 is equal to F vertical over the tension due to cable B, so therefore cable B is equal to sine 50 times by this force, which is 444.1, so it's 580.1 newtons. For the final part of the question, the horizontal component of cable A, as we've just worked out, is 508 newtons. Now the cable B tension, if you work it through, is going to be 580.1 newtons, as shown in the previous question. So therefore, 580.1 times by cos 50, which is the horizontal value, the horizontal component of cable B's tension, is going to be 372.8 newtons. So therefore, the total horizontal force is not going to be equal to 0. It's actually got a force of 135.2 newtons towards the left, indicating that we're not in horizontal equilibrium. An engineering team is stress testing a uniform horizontal steel beam of length 3 meters suspended at its center from a crane. They apply 2 vertical downwards forces at known distances from the center, simulating uneven loads. The beam remains horizontal and stationary in each case. The data below shows 2 different test configurations. For test 1, show that the moments about the center are balanced. For test 2, calculate the value of force B that we require to keep the beam in equilibrium. Then the engineering report suggests that a shift in the position of force A by 0.10 meters in test 2 would require significant recalculation of force B. Evaluate this claim and comment on the sensitivity of the balance conditions to position. So pause the video now, then unpause the video when you want to go through your answer. Right, in our first question, we can say that the clockwise moment is equal to 210 times by 1 from the information given. So therefore, it's going to be equal to 210 Newton meters. The anti-clockwise moment from the information given is 280 times by 0.75, which is 210 Newton meters. So the moments are therefore equal and opposite for test 1. So our total moment is 0. So therefore, the beam is in equilibrium and remains horizontal. For the next question, the anti-clockwise moment is equal to 300 times by 0.60, which is 180 Newton meters. So we can set this therefore equal to the clockwise moment. So therefore FB times by 1.2 is equal to 180. So therefore FB is 180 over 1.2, 150 newtons. Now the new position of force A is going to be at 0.70 meters from the information given. So our new anti-clockwise moment is force times by distance, so it's 300 times by 0.70, which is 210 Newton meters. So our required clockwise moment to create an equilibrium is 210 Newton meters. So FB in this case is going to be 210 over 1.20, which is equal to 175 newtons. So when we compare this to the original, 150 newtons, which leads to a change of 25 newtons from a 0.10 meter movement on the actual object. So this indicates that the moments are highly sensitive to the distance. A small position change can require significant force adjustments for balancing the actual object. The next question says, an experimental drawbridge section is lifted horizontally using two hydraulic arms placed symmetrically 2.4 meters apart and mounted to apply equal and opposite forces. Each arm exerts a vertical force of 4.2 kilonewtons at the same perpendicular distance from the center line of the bridge deck. A 2,500 kilogram vehicle is accidentally left parked on the right hand side of the deck, causing the bridge to tip slightly before the arms are activated. The vehicle's center of mass is located 3.6 meters to the right of the deck's center. The hydraulic system is designed to hold the deck level by producing a couple to counteract the unbalanced moment caused by the vehicle. Firstly, show that the unbalanced moment due to the vehicle about the center of the deck is approximately 88.3 kilonewton meters. Calculate the perpendicular distance from the center of the deck to each hydraulic arm if the couple they produce exactly balances this moment. Then discuss how the concept of a couple allows this system to remain stable without producing a net linear force. Evaluate why a couple rather than a single counteracting force is necessary. So, pause the video now, then unpause the video when you want to go through your answer. In our first question, we can say that the weight of the vehicle is mass times by gravity, so it's 2,500 times by 9.81. So the value for the weight is 24,525 newtons. Moment is force times by distance, so we multiply this by 3.6 meters, so we get a moment of 88,290 newton meters. Next, we know that the total moment is 2 times by 4.2 kilonewtons times by x, where x is the distance from the center to each arm. So 2 times by 4.2 times by x is equal to 88.3. So x is equal to 88.3 over 8.4. Remember, we can just cancel through these kilonewtons. Okay, so therefore it is 10.51 meters. So this indicates to us that each arm must be 10.5 meters from the center to balance the moment. Now we know that a couple will produce rotation only. The equal and opposite forces in the couple cancel linearly but will produce a net torque. So this setup avoids pushing the bridge either sideways or upwards. So a single upwards force from one hydraulic arm would produce both rotation but also lift. So in this scenario, the symmetrical couple ensures that the bridge will rotate to a level position without shifting its support base either up or down or side to side. Figure 4 shows an archer using a bow in a competition. The archer exerts a force F to pull point P on the string back through a distance S. Figure 5 is a simplified diagram of the bowstring showing the forces acting on P. The tension in the string is T and the string makes an angle of 75 degrees to the horizontal. In figure 5, F is 160 newtons and P is in equilibrium. Calculate T. So, pause the video now. Then unpause the video and you want to go through your answer. Right, we know that if it's in equilibrium, that F must equal 2 times by T cos 75, because we can see in the right hand side there's two forces acting on the right hand side to cause that equilibrium, so it's to be 2 T cos 75. Now we know that F is 160, so 160 is equal to 2 T cos 75, so therefore T is equal to 310 newtons. Consider a ladder that a person can use to climb into the roof space of a building. When not in use, the ladder is stored in the roof space and the opening to the roof space is covered by a board. The board is hinged to the ceiling at one end. The ladder is attached to the board by a rail as shown below. A small block prevents the board from rotating into the roof space. The weight of the board and the rail is 50 newtons. The weight acts at a distance of 0.45 meters from the hinge as shown. The total length of the ladder is 2.70 meters with a 0.85 meters to the left of the hinge. The weight of the ladder is 54 newtons, assume the ladder is uniform. So firstly, explain why the board and the ladder remain in the position shown. A downward force is required to rotate the board away from the block. This force is applied 0.80 meters from the hinge. Determine the magnitude of this force. So, pause the video now, then unpause the video when you want to go through your answer. So we know that the distance from the hinge to the centre of gravity of the ladder is going to be 2.7 meters. So therefore, what we can therefore say is divided by 2 or 2 minus 0.85. meters. So therefore our clockwise moment is equal to 54 newtons times by 0.50, which is 27 newton meters. The anti-clockwise moment is 50 newtons times by 0.45 meters, so it's 22.5 newton meters. This indicates to us that the clockwise moment must be greater than the anti-clockwise moment. So therefore the block will cause a force and a resultant moment. So it will cause a force or a moment. So therefore our resultant moment, on the board on the ladder is 0, explaining why we'll stay in that same position. Now we know that the resultant moment must therefore be 27 newton meters minus 22.5 newton meters, which is 4.5 newton meters. We know that force is equal to the resultant moment over the distance away from the center of mass, or the rotation point. So therefore it's 5.63 newtons. Two brackets A and B support a shelf of length 1.2 meters. Bracket A is positioned 0.15 meters from the left-hand end of the shelf. A book is placed 0.35 meters from the left-hand end of the shelf as shown. The normal contact forces of each bracket on the shelf are equal. Determine the distance of bracket B from the left-hand end of the shelf, where the weight of the book is 8.5 newtons and the weight of the shelf is 14 newtons. Bracket B is moved closer to the left-hand end of the shelf. Explain the effect on the magnitude of the normal contact force of bracket B on the shelf. So, pause the video now, then unpause the video and you'll want to go through your answer. Right, so there's a couple of ways we can work this through. We know that the total force up equals the total force down. So FA plus FB is equal to 22.5 newtons. Now we know FA equals FB, so 2F is equal to 22.5 newtons, so each F is 11.25 newtons. Now you can take your moment from either the left end, the midpoint, or taking it from A. So let's just take it from the left end because that's the easiest to work out. So we know if we take the moments from the left end, we know that the moments on the clockwise moments must equal the anti-clockwise moments. So 11.25 times by 0.15 plus 11.25 times by x is equal to 8.5 times by 0.35 plus 14 times by 0.6. So therefore x equals out to be 0.861 meters. Now, in this next question, if we move the bracket closer, the moment must be the same. So if there's a smaller distance, well then the force, because moment equals force times by distance, must increase. Now, two brackets C and D support a shelf of length 1.5 meters. Bracket C is positioned 0.25 meters from the left-hand end of the shelf. A vase is placed of 0.45 meters from the left-hand end of the shelf. The normal contact forces on each bracket on the shelf are equal. So, determine the distance of bracket D from the left-hand end of the shelf, with the weight of the vase being 12 newtons and the weight of the shelf being 18 newtons. Then, bracket D is moved closer to the left-hand end of the shelf. Explain the effect on the magnitude of the normal contact force of bracket D on the shelf. So, pause the video now, then unpause the video and you'll want to go through your answer. Once again, it's the same principle. So we take moments about bracket C to eliminate the need to consider the force exerted by C in the equation. So the position of the vase from bracket C is 0.45 meters minus 0.25 meters, so it's 0.20 meters. The moment due to the vase about C is 2.4 newton meters. Now the centre of mass of the shelf is located at the midpoint, so it's 0.75 meters from the left-hand end. So the distance from bracket C is 0.75 minus 0.25, which is 0.50 meters. The moment due to the shelf is 18 newtons times by 0.50 meters, or 9 newton meters. Now, since the normal contact forces are equal, the force on bracket D is also the same as that on bracket C. So we know that the moments must balance. So FD times by the distance from C to D is equal to the moment due to the vase plus the moment due to the shelf. So it's going to be equal to FD times by D is 2.4 newton meters plus 9 newton meters, which is 11 newton meters. Now, given that our normal contact forces are equal, we know that FD is equal to 12 plus 18 over 2, which is 15 newtons. So therefore D, the distance, is going to be the moment, which is 11.4 newton meters, divided by our force, 15 newtons, to give our answer 0.76 meters. So therefore the distance of bracket D from the left-hand end is 0.25 meters plus 0.76 meters, which is 1.01 meters. Now, moving bracket D closer to the left increases the load it supports as it's closer to the vase and the shelf's centre of gravity. Now, with bracket D being closer to the left end, it now has to support a greater proportion of the total weight. So this will increase the normal contact force on D. So as bracket D takes on a greater load, the force on bracket C decreases as it's now further from the centre of mass of the loaded shelf. A balance is formed by a beam suspended from a string. A dish is hung from the beam, and the balance is used to measure a fixed portion of rice. When the dish contains one portion of rice, the balance is in equilibrium. State the conditions needed for an object to be in equilibrium. Then the dish is moved along the beam so that the horizontal distance from the string to the dish is 7 centimeters. Rice is added to the dish until the balance is in equilibrium. Deduce whether the dish now contains 3 portions of rice. You should include a calculation of the weight of one portion of rice. The weight of the beam is 3.1 newtons and the weight of the empty dish is 0.64 newtons. So, pause the video now, then unpause the video when you want to go through your answer. Now, for an object to be in equilibrium, there are 2 conditions. The resultant force on the object is 0, and the resultant moment about the object is also 0. Now, for the next question, we know that the moment of the weight of the beam is 3.1 newtons times by 0.08 meters, which is how far it is from the center as shown in the diagram. So that's 0.248 newton meters. So we know that the moment equals force times by distance, so it's 0.248 equals the weight times by 0.25, so our weight of the dish and the rice is 0.248 over 0.25, which is 0.992 newtons. So the weight of one portion of rice by itself is 0.992 minus the weight of the empty dish 0.64, which is 0.352 newtons. So we know that moments on either side must balance. So moments are equal to 0.248 equals the number of portions times by 0.352 plus 0.64, the weight of the rice on the dish, times by 0.07. So we work it all through, we get our value to be 8.2. So the dish contains 8.2 portions of rice, not 3 portions of rice. A student abseils down the outside of a building using a rope. The mass of the student is 55 kilograms. The rope of negligible mass is attached to a fixed point X at the top of the building. The rope makes an angle of 15 degrees to the building. Firstly, calculate the weight of the student. Then determine the tension T in the rope. Then as the student abseils down the building, the angle the rope makes with the building decreases. State whether the tension in the rope increases, decreases or stays the same and justify your answer. So, pause the video now, then unpause the video when you want to go through your answer. Okay, we know that weight is mass times by the gravitational field strength. So it's 55 times by 9.8, which is 540 newtons. We can see from the diagram that the vertical value of tension is going to be T cos theta because the angle is being made with the vertical, not the horizontal. So 540 equals T cos 15. So therefore T equals 560 newtons, as shown in this diagram. Now, as the student abseils down the building, the value of tension will decrease because as the angle decreases, the cosine of the angle increases, or we could say the horizontal component of the force decreases. So therefore, this value of tension must decrease. So this brings an end to our revision session today. So if we're being successful, we should be able to answer A-level physics examination style questions, assess our understanding on A-level physics, and understand what topics we need to improve upon for A-level physics. So thank you for watching this revision session in the mechanics topic of AQA A-Level Physics on paper 1, looking at the concept of forces and moments. Thank you so much everyone, and as always, have a lovely day. Hello and welcome to this revision session for AQA A-Level Physics Paper 1, looking at the topic of mechanics. So in today's revision session we're going to look at how to answer examination questions on A-Level Physics Paper 1 in particular mechanics. So if we've been successful and we've learned in today's revision session, we should be able to answer A-level physics examination style questions, assess our understanding on A-level physics and in particular mechanics, and then understand what topics for mechanics we need to improve upon for AQA A-Level Physics. So how should you prepare for this revision session? So when you complete your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and in this left hand side section write down any working out or answers to the questions in the revision session. When you're doing this, make sure to write in full sentences and show your full working out, whilst in the right hand side write down any bits of information which you find useful or any hints and tips on answering questions from this revision session. After the revision session ends, write up these notes into a revision sheet for you to use independently. How should you be revising AQA A-Level Physics in general? Well, the first thing you should be doing is learning the key facts, so use the revision guides, the class workbooks, prep notes in the textbook to learn key ideas of the course. You may wish to make mind maps or write out notes yourself. The second step is to test yourself, is to retrieve your understanding. So use Caboodle, use Seneca, use knowledge checkers to quickly test your own knowledge, and you may wish to do this from your own cue cards. Then the third step is to practice exam style questions. So use examination preparation books, homework books, supervised study books, additional workbooks to help answer exam questions and mark your own work, and you may wish to even download your own exam past papers to do this. So the three steps will be learning the key facts, then testing yourself, and then practicing examination style questions. Now in this particular revision session we'll have three types of questions. The first type of question is a general check question, which is a basic question designed to probe your understanding of the key concepts of the topic. Then we have our checkpoint questions, which are the more challenging questions designed to place your knowledge and understanding of the topics into different contexts and applications. Then finally, the assessment point questions are past paper examination questions, which will mimic the type of questions found in the public examinations. So let's have a look at the key ideas of mechanics, starting with our general check questions. So the first question says, three coplanar forces act on an object. The vectors representing these three forces form a closed triangle. State the resultant force acting on the object. And then below shows an object in equilibrium. Firstly, draw a labelled triangle of forces. Then secondly, calculate the magnitude of force T. And then thirdly, state and explain the magnitude of the resultant of the forces 5 newtons and 12 newtons. So pause the video now, then unpause the video when you want to go through your answer. Right, for this first one, the key idea you've got to understand is if there's a closed triangle from drawing your vector diagram, well, therefore the resultant force is 0. So the overall net force will be 0. So again, with this question 2.1, because the object's in equilibrium, you should have a triangle which is drawn to scale. All the arrows follow each other head to tail, head to tail, head to tail, and you get a closed shape forming. Now, in terms of the magnitude of force T, we've got to use, because it's going to be a right angle triangle that we're going to form, we can use the Pythagorean theorem. So we can say that T squared is equal to 5 squared plus 12 squared, which therefore is the square, T is equal to the square root of 169, which is going to equal 13 newtons. Now, state and explain the magnitude of the resultant forces. Well, the resultant in any direction overall, because it's an equilibrium, must be 0. So therefore you can say that the resultant of the 5 newtons and the 12 newtons are equal to T, but therefore they're in opposite directions to cancel out to give 0. So therefore the resultant force of T to equal out that magnitude of the other two must equal 13 newtons. In our next question, the first one says the diagram below shows all the forces acting on a particle. Given that the particle is in equilibrium, find the magnitude of force P. Then secondly, the diagram shows that all the forces on the particle in equilibrium. Find the magnitude of the forces P and Q. Then thirdly, show with a vector triangle that an object is in equilibrium if only these forces are acted upon it. 12 newtons acting east, 5 newtons acting north, and 13 newtons acting 23 degrees anti-clockwise from west. And then the forces below are in equilibrium, find the magnitude of force F. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you understand that the particle's in equilibrium. So you know that the forces will form a closed loop when drawn head to tail, so you can use trigonometry. So you can see that actually it's going to be equal to 20 over cos 45, which is 28.3 newtons. Again, for this second question, we can resolve vertically and we can resolve horizontally. So vertically, you can see that the vertical component of Q is going to equal 120, and that the horizontal component of Q is going to equal P, because they've got to cancel out to give you a particle in equilibrium. So when you work it all through, you work out your vertical component of Q there, and you equate it there, so you can work it out to be equal to 156.6 newtons, and for P 100.7 newtons. Now in this next one, we will draw a scale diagram, so drawing your 12 newtons, 5 newtons, 30 newtons to scale. Because it's in equilibrium, it should form a closed triangle, because that's what objects do when they're in equilibrium. Now for the last question, again, you're going to have to resolve horizontally for F. Okay, so you can see the horizontal component of F is going to be equal to 7.1 newtons. Okay, and you can work it through like that, so you get your answer to be 16 newtons. The next question says, the diagram represents four coplanar tension forces acting on a joint in a structure. Calculate the horizontal component of the equilibrium force E. So pause the video now, then unpause the video when you want to go through your answer. Right, so what you're going to have to do is look to see the direction that all the objects are acting, and the objects acting to the left are going to have to equal the objects acting to the right, but you're also going to have to consider the horizontal component of each of those forces because they're acting at an angle. So what we can say is that 26 cos 20 plus 8 cos 70 is going to equal E cos theta plus 32 cos 60 to equal it through. We can then work through all the values and then equate it to be E cos theta, which is equal to 11.17 newtons. The next question says, below shows a meter ruler pivoted at the 50 centimeter mark. Two objects of weight 0.70 newtons and W are placed on the ruler to balance it. Assuming the weight of the ruler is negligible, calculate the size of W and the force acting on the pivot. Then for the second question, below shows a model of a loaded section of a bridge made using a uniform wooden beam. The wooden beam is 120 centimeters long and has a weight of 15 newtons. One end of the beam rests on a support and the other end is fixed to a vertical string. Calculate the vertical force R at the support. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer these questions? Well, you can see that when an object's in equilibrium, that the clockwise moment about the pivot will equal the anti-clockwise moments about the pivot, and the forces acting upwards will equal the force acting down. And those two principles are always the case when an object is balanced. So you can work out your clockwise moment by doing 0.14, converting centimeters into meters, times by that force, W, because moment is force times by distance, equal 0.70 times by 0.32. We rearrange it, make W the subject, and we get 1.6 newtons. We can then also say the total force down equals the total force up because it's balanced. So therefore, the force up, R, is equal to 0.70 plus 1.6, which is 2.3 newtons. Now in this next one, we once again use the principle that clockwise equals anti-clockwise moments. We can see that R is going to cause a clockwise moment, and you can work it through by saying R times by 1.20, because we know that it's being supported at the tension point, which is at the other end of the beam, which is 1.2 meters away, equals 15 times by 0.60 plus 13 times by 0.40. Looking at where all they are from the actual string, you can see that's their distances. So you work out R to equal 12. We then say force up equals force down. We know that there's 15 acting down. We know that there's 13 acting down. We know that there's 12 acting up from R. So therefore T must equal 16 to cancel the other two through. The next question says, a uniform cylinder has a height of 10 centimeters and a diameter of 3 centimeters. The cylinder is placed with its circular base resting on a horizontal table. Calculate the maximum angle of which it can tip before it continues to fall on itself. Then calculate the magnitude of the forces below. So pause the video now, then unpause the video when you want to go through your answers. Right, in this first one, you've got to understand that the line of action which is produced by the weight must fall below the base. So when you actually draw it out, you can see that you're going to get your right angle triangle, and you can have your opposite and your adjacent. Okay, your opposite being the diameter and the adjacent being half of the height. So you can say it's 1.5 over 5, so therefore theta equals 17. And again in the second one, it's once again these idea of moments. It's the idea that clockwise equals anti-clockwise moments. You look across here, and the difference from the previous question is that now F is at an angle, and we've got to only consider the vertical component, because it's only the vertical component of the force that is producing the moment. So we're not using F in our equation, rather we're using F sine theta. So we equate the anti-clockwise and clockwise moments, we make F the subject, we then pop in all the values, and we say F is equal to 30 newtons. The next question says, a horizontal beam carries two concentrated loads. The beam is attached to a wall by a pin joint at point A. The beam is supported by a cable between points B and C. Calculate the force F in the cable. So, pause the video now, then unpause the video when you want to go through your answer. Right, again, similarly to those previous questions, we want to look at working out the values, and we know that if it's actually in equilibrium, we know that anti-clockwise equals clockwise moment. We also know that F has actually got a vertical component, so we've got to actually work out what it would work through with the angles. So we can work out the clockwise moment. We can say that the anti-clockwise is equal to 1.2 times by F sine 35, so we can work it all through, and then F is equal to 21.06 kilonewtons. The next question says, the velocity time graph for a car travelling on a straight road is shown below. Without carrying out calculations, firstly describe how the acceleration of the car varies between t equals 0 and t equals 100 seconds. Then determine the total distance travelled by the car in 100 seconds. Then determine the average velocity of the car. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, you've got to think about what the graph shows. So for velocity time graph, the gradient shows the acceleration. So from t is equal to 0 to t equals 75, we've got a constant acceleration. Then after 75 seconds, we've got no acceleration, so a constant velocity of 15 meters per second. Now the total distance travelled is the area under the line, which is the area of the triangle plus the area of the rectangle. We work it through, we add them together, and we get 940 meters. Now we can work out the average velocity because it's going to be the displacement divided by the time. In the previous question, we worked out the displacement, which was 937.5, which we rounded to 940. We then divide by the time of the journey, which is 100 seconds, so it's 9.4 meters per second. The next question says, the velocity time graph for a sprinter running along a straight track is shown below. So calculate the total distance travelled by the runner in 13 seconds, then calculate the average velocity of the runner. So pause the video now, then unpause the video when you want to go through your answer. Right, like in that similar question, how do you work out the total distance in the velocity time graph? Well, it's the area under the line. So you can split up the area under the line into three different shapes. You've got your triangle, you've got your rectangle, and you've got your trapezium in those three different segments. So again, you work out the area of the triangle with a half base times height. We then work out the area of the rectangle with base times by height. And then again, we work out what the area of the trapezium is with a half base times height. So you work it all through and you get 100 meters. Then the average velocity again is your total displacement divided by your total time. We've just worked out that the displacement is 100 meters. We can see on the graph that the time is 13 seconds, so it's 7.7 meters per second. In our next question, it says a ball is given an initial velocity up a ramp. The subsequent motion of the ball is illustrated below. Firstly, describe the motion of the ball. Secondly, calculate the total distance travelled by the ball up and down the ramp. Thirdly, what is the average speed and average velocity of the ball between t equals 0 and t equals 8 seconds? Explaining your answer. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, it's very important you understand what the different things show. So a line sloping downwards is going to show a negative acceleration or deceleration. And when it's actually under the line, that again is a negative acceleration, but that's not a deceleration, rather that's an acceleration in the opposite direction. So the three steps are, you've got a constant deceleration, then the object will stop at 4 seconds because of v equals 0 at 4 seconds when it crosses the axis. Then after 4 seconds, it'll accelerate back to where it starts again, second by going in the opposite direction. Now the total distance is the area under the line. Now it's important to note that distance travelled is a scalar, so you would add the two sections under the line even though one is a plus and a negative because it's a scalar quantity. So you do a half base height because it's a triangle times by 2 because it's on either side of the line, so it's 16 meters. Now the average speed is the distance divided by the time, so it's 16 meters divided by 8 seconds, so it's 2 meters per second. But the average velocity is the displacement over the time. Now the displacement is a vector, so you'd have to now subtract the two values from above the line and below the line, because now the negative makes a difference because it's got a direction. So it will be 0, not 16. So 0 over 8 gives you 0 meters per second. Now, the next question says, a car is on a road with a set of traffic lights ahead. The car starts from rest and the car then accelerates at a constant rate of 3 meters per second for 8 seconds. Calculate the velocity of the car after 8 seconds. Then the car then decelerates at a constant rate of 4 meters per second squared and stops at the traffic lights. Calculate the distance travelled by the car whilst it is decelerating. So pause the video now, then unpause the video when you want to go through your answers. Right, so because we've got constant acceleration and constant deceleration, we can use SUVAT, the equations of motion, to answer this question. So you can use V equals U plus AT, because we've got U, we've got A, we've got T, and we want to work out V. So you can pop in all those values and we get 24 meters per second. And it's the same thing here, apart from now we're decelerating. So the value for A has to be a negative number because we're decelerating. So we can use the equation V squared equals U squared plus 2AS, rearrange it to get S, the displacement in this situation, which is the same as the distance travelled in this case, pop in all the values, work it through, and you get 72 meters. The next question says, tennis players can practice using a tennis ball machine. The machine projects tennis balls horizontally from a height of 2.54 meters as shown. Firstly, show that the time taken for the ball to reach the ground is about 0.7 seconds. Secondly, the ball lands on the ground at a horizontal distance of 17.89 meters from the machine. Calculate the velocity of the ball as is projected from the machine. Then, the initial velocity of the ball as it is projected from the machine can be increased. Explain how increasing the initial velocity would affect the angle at which the ball hits the ground. So pause the video now, then unpause the video when you want to go through your answer. Right, so this is an example of a projectile. So in a projectile, you've got to remember that vertically, you've got the force of weight acting down on the object. So you can work out acceleration from that. So we can just use SUVAT again, but this time our acceleration is 9.81 because it's being accelerated downwards by gravity, by its own weight. So you pop in all the values, work out T, and we get T to be 0.72 seconds. Now it's important to know that we're looking at horizontally what's going on. Now with a projectile, there are no forces acting horizontally, only vertically, so therefore you can use the equation speed equals distance over time in the horizontal. So we can say it's 17.89 over 0.72 because the time is the same both vertically and horizontally for a projected object, so we get 24.8 meters per second. Now if you think about what's going on, we've just said that the horizontal component, okay, is going to be larger because it's being projected further by the machine, which is projecting horizontally. The vertical component wouldn't be affected by this. It would still have the acceleration due to gravity on it, so you can therefore see what's happening in terms of the object's angle it hits the ground at. The next question says, firstly, state Newton's third law of motion. Then the figure below shows a satellite in orbit around the Earth. Show the force to act on each body, and then state 3 properties of these forces that show them to be a Newton's third law pair. So pause the video now, then unpause the video when you want to go through your answer. Right, it's very important you understand Newton's third law of motion. It states that if a body A exerts a force on body B, then body B will exert an equal and opposite force of the same type on body A. So in the diagram, there will only be one force on each body, the force from the centre of the satellite towards the centre of the Earth, and a force from the centre of the Earth towards the centre of the satellite, and they're both being gravitational attraction. Now, what properties indicate that something is a Newton's third law pair? Well, they'd have the same type of force, gravitational, the same magnitude, they'll act in opposite directions and act on 2 separate bodies, the Earth and the satellite. The next question says, the photograph shows a rocket. The rocket is launched vertically. The rocket's engines give a total upwards thrust of 7.3 times 10 to the 7 newtons. Calculate the initial acceleration of the rocket with the mass being 5 times 10 to the 6 kilograms. Then give one reason why the acceleration will increase as the rocket rises. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, we're looking at Newton's second law, which is F equals ma. But F is the resultant force. So whilst there is a force acting upwards of thrust, there's also a force acting downwards of weight because it has a mass. So you work out that value of weight by doing mass times by gravity. You can then find out the overall resultant force by subtracting the thrust, so the weight from the thrust. So we get a value out there to be 2.39 times 10 to the 7 newtons. Acceleration is force over mass, so we get 4.78 meters per second. Now the acceleration will increase because as the object rises, the mass will decrease because fuel is used up. So therefore the thrust force will overall increase and the resultant force overall will increase. Let's now have a look at some checkpoint questions. So the first question says a force of 10 newtons acts on an object at an angle theta to the horizontal. Calculate the horizontal components of the force when theta equals 0, 45 and 90 degrees. Then a parasender is attached by a rope to a boat travelling at a constant velocity. The rope is angled at 35 degrees to the surface of the sea and the tension in the rope is 1650 newtons. Calculate the horizontal and vertical components in this rope. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we've got to remember how to work out the horizontal component when you've got an angle at the horizontal, So therefore, it's actually the horizontal component is F cos theta. So it'll be 10 cos 0, 10 cos 45, 10 cos 90. That comes from the triangle that will be produced. And again, if you look at this idea that the angle is at 35 degrees to the surface of the sea, to the horizontal, we can say the horizontal is F cos theta and the vertical is F sin theta, and you can work out your two components that way. So you get 1352 newtons horizontally and 946 newtons vertically. The next question says, some students used a plank to make a bridge to cross a stream. The plank rested on a rock and a wall as shown. The plank is uniform. Firstly, show that the weight of the plank is about 250 newtons, with the mass of the plank being 25 kilograms. Determine the force exerted by the wall on the plank, and then a student of weight 550 newtons states that the plank will tip if she walks from the rock to the other end of the plank. Justify the student's statement. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, it's a really nice one. Weight is mass times by gravity, we get 245 newtons. The next one is you're looking at this object here, and because we've worked out a weight, the weight must be acting from the dead center downwards, which is 2.5 meters from either end. Okay, so therefore we can say that when we balance our moments now, because it's at rest, so therefore it's in equilibrium, we can say clockwise moments equals anti-clockwise moments. So it's 245, the weight, times by 2.5 meters, because it's acting on the dead center, equals F times by 3.6 meters, because that's how far away it is from the edge. So we get F to be equal to 170 newtons. Now, will it tip over? I think the best way to work it through is what is actually the moment you're producing, which is right at the other end of the plank, because that'll be the biggest moment. So you can say, well, it's actually going to be 550 newtons, which is her weight, times by 1.4, which is how far she can get away there. So she would get away to be 770 newtons. That's much larger than the 270 newtons produced on the other side. So therefore there's going to be a result moment, and that will cause the plank to tip. The next question says, the diagram shows a crane lifting a load. There's a large mass called a counterweight attached to the crane on the opposite side of the tower to the load. The horizontal distance from the load to the tower can be changed, and the horizontal distance from the counterweight to the tower can also be changed. Explain how the counterweight needs to move when the load is moved away from the tower. The beam is uniform with a weight of 3 times 10 to the 4 newtons, and the counterweight has a weight of 1.1 times 10 to the 5 newtons. The load has a weight of 4.4 times 10 to the 4 newtons. Deduce whether the load can be moved to the end of the beam without the crane toppling. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you've got to understand what's going on to the principle of moments. So the total clockwise moment must balance the total anti-clockwise moment, so the overall moment is 0. So that the anti-clockwise moment is due to the counterweight, and the total clockwise moment is due to both the weight of the beam and the load that's acting on it. So if you increase the distance of the load, you'll increase the moment, because it's force times by distance. So therefore the distance of the counterweight also needs to increase the moment to balance it, because moment is force times by distance. Now in this next one, like we said, moment is force times by distance. We know where the centre of mass of the beam is going to be, so we can therefore use the principle of moments to equal that they must balance if it's going to actually work. So you pop in all the values, the anti-clockwise moments and the clockwise moments. You can look at the diagram to see if it's going to cause a clockwise or anti-clockwise moment. You then work out x to be 15.2 meters. Now 22 meters is the total distance it could possibly move on the crane, but after 15.2 meters it's no longer going to have a result. It's going to no longer be balanced because there's going to be a resultant moment. So therefore, if the beam was moved past 15.2 meters, there will be a resultant moment and the crane would topple. The next question says, a car is initially stationary. It has a constant acceleration of 2 meters per second squared. Calculate the velocity of the car after 10 seconds. Calculate the distance travelled by the car at the end of the 10 seconds. Calculate the time taken by the car to reach a velocity of 24 meters per second. Then in another example, a train accelerates steadily from 4 meters per second to 20 meters per second in 100 seconds. Calculate the acceleration of the train. From its initial and final velocities, calculate the average velocity of the train. And then thirdly, calculate the distance travelled by the train in a time of 100 seconds. So pause the video now, then unpause the video when you want to go through your answer. Once again, it's about constant acceleration, so we're using the equations of motion. We're using SUVAT. So the first one, v equals u plus at. Remember, it's initially stationary, so u equals 0 to get 20 meters per second. The second one, we can say s equals ut plus a half at squared. Once again, u is starting off as 0 because it's stationary, so you get 100 meters. And then rearrange v equals u plus at to get t equals v minus u over a, and we get 12 seconds out. In the next question again, a is equal to v minus u over t. You've got v, you've got u, you've got t in the information, so you get 0.16 meters per second. Now, the average velocity is the mean of the initial and the final, so it's the initial and the final added together, divided by 2, so we get 12 meters per second. And then the distance travelled by the train in this time is going to be, if you think about it, it's working through to be speed is distance over time. So therefore we can say distance is speed times time when we're using the average speed, so it's the 12 times by 100, it's 1,200 meters. In the next question, a car is moving at 8 meters per second. The driver makes it accelerate at 1 meter per second squared for a distance of 18 meters. What is the final velocity of the car? The second question says trials on the surface of a new road show that when the car skids to a halt, its acceleration is minus 7 meters per second squared. Estimate the skid to stop distance of a car travelling at a speed limit of 30 meters per second. And then at the scene of an accident on a country road, police find skid marks stretching for 50 meters. Tests on the road surface show that a skidding car decelerated 6.5 meters per second squared. Was the car which skidded exceeding the speed limit of 25 meters per second on this road? So pause the video now, then unpause the video when you want to go through your answer. Right, again, we're using SUVAT because we've got constant acceleration or deceleration. So this first one, we can use v squared equals u squared plus 2as because we've got all the information there. We can then work out what our value is going to be for v by doing the square root of u squared plus 2as, pop in all the values as shown on the screen, and we get 10 meters per second. In this next one, we're looking at distance. So again, we can say s equals v squared minus u squared over 2a. We know that v is u because it's stopped. Okay, we know that v is 0, because it's stopped, and u is 30 because it tells you in the question. You've got acceleration to be minus 7, so you can work it all through, and we get 64 meters. The next one, again, we're trying to work out if it was above the speed limit. So we're trying to work out the initial velocity. Now we know the final velocity is going to be 0 because it's stopped moving. We know that acceleration is minus 6.5 because it's decelerating. So we pop those into the SUVAT equations and we get 25.5 meters per second. So we give our conclusion it was just above the speed limit. The next question says, a vehicle accelerated from 13.4 meters per second to 22.3 meters per second in 8 seconds. Calculate the distance travelled. Then a runner changes her velocity from 3.2 meters per second to 4.2 meters per second. In this time, she travels 200 meters. Calculate her acceleration. Then in 2009, Usain Bolt sprinted 100 meters in 9.58 seconds, setting a new record. If he travelled at a constant acceleration from start to finish, what's his acceleration? Then a dragster travels 0.25 miles in the time of 4.6 seconds along a straight track from a standing start. 1 mile is 1,600 meters, so calculate its acceleration and final velocity. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first one, we're using suvat again. So again, we know that we want to work out S, so it's a half U plus V times by T. Pop in all the values and we get 155 meters. Once again, suvat, but this time we're doing V squared equals U squared plus 2AS. Pop in all the values, make A the subject, and we get 0.019 meters per second squared. The next one again, we're using a suvat of S equals UT plus a half AT squared. We can make A the subject by doing 2S over T squared, pop in our values and we get 2.2 meters per second squared. Then again, we're using suvat with S equals UT plus a half AT squared. Make A the subject, sub in all the values and we get 38 meters per second squared. And we then use V equals U plus AT to work out what V would be, and that's 170 meters per second. The next question said a boy was throwing a ball towards a wall. The wall was 5 meters from the boy, and the top of the wall was 3 meters above the point where the boy released the ball. The boy tried to throw the ball over the wall, but sometimes the ball hit the wall. In one attempt, the boy threw the ball with an initial velocity of 9.70 meters per second at an angle to the horizontal of 49 degrees. That showed that the ball traveled the distance to the wall in about 0.8 seconds, and then deduce whether the ball went over the wall for this attempt. So pause the video now, then unpause the video when you want to go through your answer. Right, again, it's a projectile question this time, so the only force acting upon it is the force of weight acting downwards in the vertical. So what can we do? Well, we can use the horizontal. Remember, the horizontal, there's no forces acting on it, so we can use the equation speed equals distance over time. So time is going to be equal to distance over speed, but we've got to work out the horizontal component of that velocity. So it's 9.7 cos 49 to get to be 6.36, and we say time is 5 over 6.36, so it's 0.786 seconds. Now, in this particular attempt, did it go over the wall? Well, we've got to look at its vertical displacement. So we've got to use suvat and work out what the value of S is. So we can say, well, S equals UT plus a half AT squared. Now, remember two things. Firstly, we're looking at the vertical velocity. So we're going to have to resolve 9.7 into its vertical velocity. So it's 9.7 sine 45. And secondly, the acceleration is against gravity because it's going upwards and gravity acts downwards, so it's minus 9.81, so we get 2.72 meters, which is less than 3 meters, so it doesn't go over the wall. The next question says a cannonball is fired horizontally from a cliff top 44.1 meters above the sea. The initial horizontal velocity of the cannonball is 304 meters per second. Calculate the time of flight, the horizontal distance it travels. Then an arrow is fired horizontally at 49.2 meters per second from a 29.4 meter high castle. Calculate the resultant velocity when it hits the ground. And then a ball is kicked with an initial velocity of 15 meters per second at an angle of 30 degrees to the horizontal. Calculate the range of the ball. So pause the video now, then unpause the video when you want to go through your answer. Right, again, we're looking at projectiles, so if we look at the vertical, we can say that S equals UT plus a half AT squared. U will be 0 because it's vertically got no velocity at the start because it's only got horizontal velocity. So acceleration is G because it's being accelerated down by gravity. So we can say it's a half GT squared. Rearrange it, make T the subject. Remember, G is 9.81, so we work it out ultimately for T equals 3 seconds. Now the horizontal distance, we know again there's no acceleration in the horizontal direction. Speed is equal to a horizontal velocity times by time, so it's 304 times by 3, 912 meters. In this next question, we can work out the vertical motion by doing V squared equals U squared plus 2AS. Remember that when we're working it through, it's starting off with no vertical velocity because it's fired horizontally, so U is equal to 0. A is going to be 9.81 because it is gravity that's acting upon it, so V equals 24. In the horizontal, there's no acceleration because there's no resultant force, so the horizontal velocity is going to remain at 49.2 meters per second. So the resultant overall velocity is by Pythagoras, horizontal and vertical components there. So it's V squared equals it's going to be horizontal squared plus vertical squared. So you work it through to be 54.7 meters per second, and you can work out your angle by doing again trig from the triangle level form by doing tan opposite over adjacent, so it's 26 degrees to the horizontal. Once again, what's the range of the ball going to be? Well, we know from the vertical motion that v equals u plus at, because we're going to use suvat in the vertical. We can resolve that initial velocity into the vertical component to be 15 sine 30, so we can work out t to be 1.53 seconds. T will be the same both horizontally and vertically, so now horizontally v is 15 cos 30, but we've resolved it in the horizontal, so s equals ut, so it's 13 times by 1.53, the time being the same in both the horizontal and the vertical, so the answer is 20 meters. The next question says, an archer fires an arrow horizontally at 110 meters per second at a target situated 50.0 meters away. The arrow leaves the bow at a vertical height of 1.6 meters. The top of the target is 12 meters above the ground and the bottom of the target is 0.40 meters above the ground. Calculate where the arrow hits the target. Then a plane is dropping with a constant horizontal velocity of 400 meters per second at a height of 250 meters. A box of emergency supplies is dropped vertically from the plane. So calculate the time taken for the box to reach the ground, calculate the horizontal distance between the point where the box is released and the point where it lands, how the force horizontally is the plane from the box to when the box hits the ground, assuming the plane continues to fly at a constant velocity, how far vertically is the plane from the box when the box hits the ground, assuming the plane continues to fly at a constant velocity. Then third question, a football of mass 400 grams was thrown from a height of 2.4 meters with a velocity of 12 meters per second at an angle of 35 degrees above the horizontal. Calculate the horizontal component of the initial velocity of the ball, the vertical component of the initial velocity, the maximum vertical height above the ground reached by the ball, and the time of flight for the whole trajectory and the horizontal range of the ball when it hits the ground. Pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, again, we can do horizontally. Again, horizontally, we've talked about this before. Time is going to be distance over the horizontal velocity. 50 over 110 is 0.45 seconds. So we can now do vertically. We can say the only force is acceleration due to gravity. So therefore, A is going to equal G, which is 9.81. It's going to be negative 9.81 because it's going upwards. Okay, so therefore, you'd work it through to be minus 1.002 meters. So the dart hits at about 0.598 meters because it's 1.6 minus 1.002 because it's going downwards, so therefore it's 0.19 meters above the bottom of the target when you look at all the logic of it. The next question, vertically, there's acceleration due to gravity, so we use suvat, so S is equal to a half gt squared, rearrange for t, pop in the values, G is 9.81, so you get 7.14 seconds. Horizontal distance, well, there's no force horizontally. Distance is velocity times by time. 400 times by 7.14, 2,856 meters. Again, horizontally, there's no resultant force, so there's 0 meters horizontally between them because there's been no acceleration at any point. So they're traveling at the same velocity. But vertically, there is going to be a issue because since the plane's flying horizontally and there's no vertical acceleration, the vertical distance between the plane and the box remains constant. The initial vertical separation is the height of the plane, so therefore when the box hits the ground, the vertical distance between the plane and the box is still going to be 250 meters. In question 3, a horizontal component is going to be v cos theta because it's the angles to the horizontal, so we work it through to be 9.86 meters per second. Vertically, it's v sine theta, so 6.86 meters per second. The maximum height, well, we can say v squared equals u squared plus 2as, so for s equals v squared minus u squared over 2a. Now at the maximum height, v is equal to 0 because it's at the maximum height, so it hasn't got any more velocity. We pop in all the values. Remember, it's going upwards, so now a is minus 9.81 because it's against gravity, so we get 2.4 meters. It's already 2.4 meters above the ground when it starts, so therefore it's now 4.8 meters above the ground. Now the time taken for the flight, well, vertically we know that v equals u plus at, so t equals v minus u over a, so we can pop in all the numbers. Remember, a is minus because we're going upwards, so it's 0.7 seconds. Now we know that the time taken to reach the peak is a third of the journey, as it's travelled 2.4 meters to be 4.8 meters above the ground, so therefore the time taken in total is going to be 3 times 0.7, so it's going to be 1.7 seconds. Now, horizontally, distance is speed times by time, so it's 9.86, the horizontal velocity, multiplied by the time, which is constant for vertical and horizontal, so it's 1.70 seconds, so it's 16.6 meters. The next question says, a student of weight 600 newtons is standing on a weighing scales in a lift. The scales are calibrated to give readings in newtons. The lift moves upwards at a constant velocity, then decelerates to rest. As the lift moves, the student looks at the readings on the scales. Explain the readings on the scales. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question you've got to remember that the force of the lift and the scales on the student is the reading on the scales, or it's the reaction force, which is the scale, or reading on the scales. At a constant speed, the resultant force on the student is going to be 0, so weight equals reaction force. So at a constant speed, the reading on the scales will just be the weight, so it'll be 600 newtons. But as the lift decelerates, the reaction will be less than the weight now, so as the lift decelerates, there's the resultant force downwards on the student, so as the lift decelerates, the read on the scales will now be less than 600 newtons because the upward force on the student is now less than his weight. The next question. A railway engine is pushing a truck along the horizontal rails at a constant velocity as shown. The engine exerts a forward force of 1.2 times 10 to the 5 newtons on the truck. The engine also exerts a net backwards force of 1.5 times 10 to the 5 newtons on the rails. Firstly, complete the free body force diagram to show all the forces acting on the engine, and then a student suggests that the weight and the normal reaction force form a Newton's third law pair of forces. Explain why the student's suggestion is not correct. Refer to the features of a Newton's third law pair of forces. So pause the video now, then unpause the video when you want to go through your answer. Right, remember when you draw a free body diagram, the length of the arrow shows the size of the force. So you'll see here that the force from the rails is going to be larger than the force from the truck when you actually look at the situation going on. Now, as well, there'll be a force of air resistance acting against the motion of the object. So as a result, you can see it working through there. Now, it's not going to be a Newton's third law pair because a Newton's third law pair of forces has force of equal magnitude in opposite directions with the same type of force acting on two different bodies. Now, firstly, the two forces act on the same thing, one body, the engine, and secondly, it's two different types of forces, gravitational and contact, so there can't be a Newton's third law pair. The next question says the engine of a motorboat provides a constant horizontal force. As the velocity of the boat increases, the resultant horizontal force on the boat decreases. Eventually the boat will travel at its terminal velocity. The constant horizontal force from the engine is 5.5 kilonewtons. Firstly, state what is meant by the resultant force. Then, at a certain time, the drag force on a boat is 3.1 kilonewtons. Calculate the acceleration of the boat at this time. The mass of the boat is 7.5 times 10 to the 3 kilograms. Then the terminal velocity of the boat is 4.8 meters per second. Calculate the output power of the engine. So pause the video now, then unpause the video when you want to go through your answer. Right, a resultant force is the vector sum of all the forces acting on the object. It's the single force which has the effect of all the other forces acting together. Now this next one, we're doing F equals ma, but remember it's the resultant force, so it's 5.5 minus 3.1 times by 10 to the 3, because it's kilonewtons, equals 7.5 times 10 to the 3 kilograms times by A, so A is equal to 0.32 meters per second squared. Now we can work out output power, because power is equal to force times by velocity. Now the force of the actual engine acting on itself is 5.5 times 10 to the 3 newtons, because we're not looking at the power of the boat, we're looking at the power of the engine, so it's the force of the engine times by that velocity of the engine, which will be the same as the boat because they're moving together, so it's 4.8 meters per second, so it's 2.64 times 10 to the 4 watts. The next question says, in each of the examples, explain whether any work is done by the force mentioned. Pulling a heavy sack along a rough ground. The force of gravity pulls you downwards when you fall off a wall. The tension in a string pulls a stone when you whirl it around in a circle at steady speed. The contact force of the bedroom floor stops you from falling into the room below. Then secondly, a man of mass 70 kilograms climbs a stairs of vertical height 2.5 meters. Calculate the work done against the force of gravity. Then a stone of weight 10 newtons falls from the top of a 250 meter high cliff. Calculate how much work is done by the force of gravity in pulling the stone to the foot of the cliff and how much energy is transferred to the stone. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, yes, there will be work being done because there's forces. The work is being done against friction because it's being pulled along that rough ground. Again, yes, gravity is doing work to make you go faster. The third one, no, because it's moving at a steady speed, so therefore it's at a constant distance from the center of the circle, so therefore there's no work being done. And then the third one, again, no work is being done because you're not moving. There's no displacement. Now, what's the work done here? Work done is force times by displacement, which is mg times by displacement. Pop it all through and you get 1200 joules. Again here, work done is force times by displacement. It's 10 times by 25. It's 2500 joules. So how much energy is transferred to the stone? Well, if we ignore any work dissipated to the surroundings, it'll be that value of 2500 joules. The next question says, a car engine does 4,200 kilojoules of work in 1 minute. Calculate its output power in kilowatts. Then a particular car engine provides a force of 700 newtons when the car is moving at its top speed of 40 meters per second. Calculate how much work is done by the car's engine in 1 second. State the output power of the engine. And then in an experiment to measure a student's power, she times herself running up a flight of steps. Use the data to work out her useful power. Number of steps, 28. Height of each step, 20 centimeters. The acceleration is 9.81 meters per second. The mass of the student is 55 kilograms and the time taken is 5.4 seconds. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, with power is work done over time. It's 4,200 times 10 to the 3, because it's kilojoules, divided by 60 seconds, so it's going to be 70,000 watts. Work done is force times by displacement, so it's force times by speed there, so it's going to be 700 times by 40, so therefore it's 28,000 joules. The output power is therefore going to be in 1 second, so it's 28,000 over 1, so it's 28 kilowatts. Our work here is being done against gravity, so it's force times by displacement in this context, so therefore it's going to be 55 times by 9.81 times by 28 times by 0.2, which is 3020. Power is work done over time, so it's then divided by 5.4 seconds to be 560 watts. The next question says, consider a ladder that a person can use to climb into the roof space of a building. When not in use, the ladder is stored in the roof space and the opening to the roof space is covered by a board. The board is hinged to the ceiling at one end. The ladder is attached to the board by a rail as shown below. A small block prevents the board from rotating into the roof space. The weight of the board and rail is 50 newtons. The weight acting on a distance from 0.45 meters from the hinge is shown. The total length of ladder is 2.70 meters with 0.85 meters to the left of the hinge. The weight of the ladder is 54 newtons and the ladder is uniform. Explain why the ladder and the board remain in the position as shown, and a downwards force is required to rotate the board away from the block. The force is applied 0.80 meters from the hinge. Determine the magnitude of the force. So pause the video now, then unpause the video when you want to go through your answers. In this first one, it's the idea it's going to be in equilibrium ultimately. So if you work out the distance from the hinge to the center of gravity, you can work it through, and therefore you can work out your clockwise moment to be 27 newton meters, because you can do force times by distance. Then you can work out your anti-clockwise moment by doing 50 times by 0.45 meters to get 22.5 newton meters. So from that you can see straight away that there's a clockwise moment greater than the anti-clockwise moment. So what's happening is the block needs to be there to produce another value for your anti-clockwise moment, so therefore the overall moment is going to be equal, so the overall moment is 0 because the clockwise moment is going to equal the anti-clockwise moment. So how can you work it through? So if you work out overall your resultant moment, you get it to be 4.5 newton meters. So therefore what force is required from this block? Well, we know that moment is force times by distance, so therefore we've got our overall moment needed to make sure it equals 0 to be 4.5 divided by your distance is 0.80 meters, so we get 5.63 newtons. The next question says, the crossbar challenge is a football contest in which competitors try and hit the crossbar of a goal by kicking a football from the penalty spot. The horizontal distance between the penalty spot and the crossbar is 11 meters. One competitor kicks a football with an initial velocity of 17 meters per second at an angle of 24 degrees to the horizontal. The football hits the crossbar. The effects of air resistance can be ignored. Firstly, calculate the horizontal component of the initial velocity of the football. Then calculate the vertical component of the initial velocity of the football. Show the time taken for for the football to travel from the penalty spot to crossbar is 0.71 seconds. The football is at a maximum height at its trajectory when it hits the crossbar. Calculate the height above the ground at which the football hits the crossbar. Then the next time the competitor tries to challenge, they kick the football at the same angle with an initial speed less than 17 meters per second. Stay where the football will hit the crossbar, pass over the crossbar, or pass under the crossbar, and justify your answer. So pause the video now, then unpause the video when you want to go through your answer. Right, we can work out the horizontal component because it's F cos theta. We can work out the vertical component because it's F sine theta, so we can work them through there. Time taken, we'll look here really at the values given. So the horizontal is probably the one we want to look at because it's easy to work through. So horizontally, time is speed over velocity. We've got our horizontal distance, we've got our horizontal speed, so it's 0.17 seconds. Then we can use for the next one the vertical, so therefore we've got to use suvat because there's a resultant force on it. So S equals ut plus a half at squared. A is minus 9.81 because it's going upwards against gravity, so we get our answer to be 2.4 meters. Now in the next one, it'll pass under the bar because the ball has a smaller vertical component of the velocity, so therefore when you look at the equation, it won't reach the same height because its velocity will be lower. The next question says, a trebuchet is a medieval catapult designed to project a rock over large distances. The simplified diagram of a trebuchet is shown. A rock is held in a sling. When the peg is removed, the counterweight falls and the rock is projected through the air. A student assumes that all the gravitational potential energy is transferred from the counterweight to the kinetic energy of the rock. Give 2 reasons why this is not correct. The rock was projected with a velocity of 41.5 meters per second at an angle of 30 degrees to the horizontal. The diagram shows the flight of the rock after it's left the trebuchet. The rock rises to a maximum height and then falls back to the same height as it releases height. At its release height. Calculate the horizontal distance travelled by the rock in this time. Then, the mass of the counterweight was reduced. The trebuchet was then used to project the rock again. Explain why the horizontal distance travelled by the rock decreased. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, it won't do because the beam will gain kinetic energy and also gain gravitational potential energy, and also some work will be done against friction, so this energy will be dissipated to the surroundings. Now, how can you work this through? The next question, well, you can work out your vertical velocity and your horizontal velocity. Vertically, we use suvat, v equals u plus at. We know that v is going to equal 0, so we can work out t to be 2.12 seconds. Time is the same horizontally and vertically. We've got the horizontal velocity as 35.9 meters per second, so therefore we can say distance horizontally is the speed times the time. We've got the time, we've got the speed, we've also had to double the time, by the way. You'll notice that because that's the value to the maximum height, and then the overall length is the time, is going to be the time to the maximum height doubled because it's been reflected back down now, so we get our answer to be 152 meters. Now in the last question, the counterweight transfers less gravitational potential energy, so the transfer of kinetic energy to the rock will be reduced. So when released, the rock has a smaller vertical velocity, so the time of flight will be reduced, and there'll be a smaller value for the horizontal velocity as well. So, thank you very much for carrying out this revision session. If you've been successful in this revision session, you should be able to answer A-Level Physics examination style questions, assess your understanding on A-Level Physics, and understand what topics you need to improve upon for A-Level Physics. Thank you so much for listening to this physics revision session on mechanics. Hope you found it very useful, and as always, have a lovely day. Hello and welcome to this revision session, which is on the mechanics topic for AQA A-Level Physics. So in today's revision session, we're going to try and look at how you can answer examination questions for the A-Level Physics topic mechanics. So into this revision session, if we're being successful, we should be able to answer A-Level Physics examination style questions, assess your understanding on A-Level Physics, and understand what topics you need to improve upon for your A-Level Physics examinations. So how would you carry out this particular revision session? So when completing the work in your revision session, divide your piece of paper into 2 sections. Make the section on the left hand side larger than that on the right hand side. Now in the left hand side section, write down your working out or answers to the questions in the revision session. Now when you're doing this, try to write in full sentences and show your full working out. Whilst on the right hand side, write down any pieces of information which you find useful or any hints and tips on answering questions from this revision session. At the end of this revision session, write up the these notes into a revision sheet for you to use independently. So what tips would I have for you to revise A-Level Physics? So the first step I would suggest that you do when you're revising A-Level Physics is to learn the key facts. So use your revision guides, your class books, your prep notes, the textbook to learn the key ideas of the course. And to do this, you may wish to make mind maps or write out the notes yourself. The second step is to then test yourself. So use things such as Caboodle, Seneca and Knowledge Checker to quickly test your own knowledge, and you may wish to do this from cue cards. Then the third step is to practice examination style questions. So use exam prep books, homework books, supervised study books, additional workbooks to help answer exam questions and mark your own work, and you may wish to download your own exam papers to do this. So you should be, if you're independently revising your A-Level Physics, is learning the key facts, testing yourself and then practicing the exam style questions. So let's start off with a few multiple choice questions in mechanics. So a conveyor belt raises 20 boxes, each of mass 60 kilograms, through a vertical height of 12 meters every 30 seconds. The conveyor belt operates at a steady speed. What is the useful output of the conveyor belt? So pause the video now, then unpause the video when you want to go through your answer. Right, so the answer for this one is B, because we know power is work done over time. Now work done is the force times by the displacement in the direction of the force. So you can say power is force times by distance over time. Now the first thing you've got to note in this question is you're given the mass in kilograms. So because it's moving a vertical height, therefore the force is going to be the weight of the object. So you do 60 times by 9.81. Now also note in this calculation we have times by 20 because the 20 boxes being raised, each with a mass of 60 kilograms, and then obviously we times it by 12 because that is the vertical displacement, then dividing it by 30 because that's how long it took. So therefore we've worked out our useful power out to be 4.7 kilowatts. Let's have a look at the next question. A lamp has a useful output power of 8 watts and an efficiency of 12%. What is the input power to the lamp? So pause the video now, then unpause the video when you want to go through your answer. Right, for this one, the answer is C, because we know our equation for efficiency. Efficiency is useful power out or energy out divided by total power or energy in. So therefore we rearrange the question and we put total in to be the subject. So we say total in is useful out over efficiency, and we pop our numbers in. Now again, remember when we're using this equation, it's important to convert your percentage back into a fraction or a number between 0 and 1. So 12% becomes 0.12. So the total in is 8 over 0.12, which is 67 watts. The answer is C. Let's have a look at the next question. What is the relationship between the momentum P of a ball falling freely from rest and time t? So pause the video now, then unpause the video when you want to go through your answer. Right, so for this one, our answer is C, because as we'll be aware, momentum is mass times by velocity. Now, if you can't remember that, that equation is found in the back of the exam paper in the equation booklet. Now, as the velocity increases, the momentum will increase for the same mass in direct proportion. Now, as an object falls from rest, the velocity is directly proportional with the time taken to fall, because the longer it falls, the faster its velocity, because we know it's accelerating due to gravity, which is a constant in this situation. So therefore P is going to be proportional to T. Let's have a look at our next question. Which of the following is a statement of Newton's third law of motion? So pause the video now, then unpause the video when you want to go through your answer. Right, so in this one, the answer is D. Now, it's very important that you've got to be aware of what Newton's third law of motion is. The first thing to note for the third law of motion is it's always between two objects interacting with each other. Now, when two objects interact, okay, that they'll exert, okay, an equal yet opposite force on each other. So when X interacts with Y, they'll exert a force on each other, okay, and that force will be of equal size, it will be in the opposite direction, and it will be the same type of force. Let's have a look at our next question. When a ball is thrown into the air at an angle to the vertical, which of the following is true? So pause your video now, then unpause the video when you want to go through your answer. Right, so what is our answer here? Well, the answer is B, because if you notice all the different options here, the force on the ball are balanced when it's its highest point. That's not going to be the case in particular instant, because at that point it's going to start to instantaneously come back down and accelerate down. The ball's acceleration increases when it starts to descend. Okay, well, again, how do we know that is that going to be the case? Well, we don't, but what we do know is that the vertical velocity of the ball is 0 at its highest point, because when it's at its highest point, it'll instantaneously stop moving and then come back down, so therefore our answer is B. Let's have a look now at a few longer questions on the mechanics topic. So, a spacecraft entering the atmosphere of Mars must decelerate to land undamaged on the surface. Figure 1 shows the spacecraft of total mass 610 kilograms entering the atmosphere at a speed of 5.5 kilometers per second. Calculate the kinetic energy of the spacecraft as it enters the atmosphere. Give your answer to the appropriate number of significant figures. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do we answer this question? Well, the first thing to note is we've got to know the equation for kinetic energy. So you know that kinetic energy is a half times by mass times by velocity squared. Now we know what our mass is, we're given it in the question. If we look, it's 610 kilograms. What's our velocity? Well, we know it's 5.5 kilometers per second. Now the trick here is, if we want to get our answer out in joules, we'll have to turn that into meters per second. So we'll be using 5,500 meters per second, because kilo means times 10 to the 3. We pop our numbers in, and you'll notice that in the numbers given in the exam question, we've got 2 sig figs for 5.5, and we've got either 2 or 3 sig figs for 610. So we go with the lowest possible value, which is 2. So we should give our answer to 2 significant figures, and we get 9.2 times 10 to the 9 joules. Right, let's have a look at our next question. So a parachute opens during the spacecraft's descent through the atmosphere. Figure 2 shows a parachute spacecraft system with the open parachute displacing the atmospheric gas. This causes the system to decelerate. Explain with reference to Newton's laws of motion why displacing the atmospheric gas causes a force on the system and why this force causes the system to decelerate. So pause the video now, then unpause the video when you want to go through your answer. Right, so it's very important that when we answer questions like this, we look at the labels given in the exam question and use this to help formulate our answer. Now, the first thing to note is that we've been given the direction of travel, and we've also been given the displacement of the gas. So let's link this into Newton's laws of motion. So why is there a force on the gas? Now, it's really important that you should really either give your understanding of Newton's laws in either momentum or resultant forces. So the first thing to note is that from Newton's second law, a change in momentum will produce a resultant force, or vice versa. So we know that the gas's momentum is changing. We know that because it's being displaced, so therefore this requires a force due to Newton's second law. Or you could say because the gas is being accelerated, that's also producing a resultant force. Now, the gas exerts a force on the parachute. Okay, so therefore we've now got two objects here. We've got the gas, we've got the parachute. So via Newton's third law, okay, the parachute will exert a force on the gas because the gas is exerting a force on the parachute of equal size, of the same type, but in the opposite direction. Now, what the next thing is, why will the system decelerate? Well, we know that things will accelerate or decelerate with a change in momentum or a resultant force. So you know it's decelerating because the resistive force is greater than the force causing it to come to the ground, which is the weight. So there's the resultant force in the opposite direction to the motion. Now, Newton's first and second law state that acceleration is always in the same direction of the resultant force, so therefore it will slow down. Let's have a look at our next question. As the parachute and spacecraft system decelerates, it falls through a vertical distance of 49 meters and loses 2.2 times 10 to the 5 joules of kinetic energy. During this time, 3.3 times 10 to the 5 joules of energy is transferred from the system to the atmosphere. The total mass of the system is 610 kilograms. Calculate the acceleration due to gravity as it falls through this distance. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do we answer this question? So the first thing you've got to be aware of is working out what our work done in our system is. So we start off with, well, 3.3 times 10 to the 5 joules. Okay, we finish with, we lose 2.2 times 10 to the 5. So therefore we've had a difference of 1.1 times 10 to the 5. So therefore we can say that this is going to be the work done due to the change, so due to the movement. So that's going to be the potential energy. So we can therefore say EP is equal to mgh, and we know that EP is going to be 1.1 times 10 to the 5 joules, because that's our potential energy, because it's changed there. So therefore if we say equals mgh, we can therefore make g the subject, pop our values in, and we get 3.7 meters per second as our answer. Let's have a look at our next question. Dust from the surface of Mars can enter the atmosphere. This increases the density of the atmosphere significantly. Deduce how an increase in dust content will affect the deceleration of the system. So pause the video now, then unpause the video when you want to go through your answer. Right, so how will you answer this question? So you've got to understand what density is. So density is how many particles there are in a certain volume. So if we've increased the density, that means that there are more particles in a certain volume. Now in our previous questions, we've understood that the parachute is displacing the gas, so it's moving the particles of the gas to a different place. So therefore, if the density has gone up, more mass is there to displace, so there's more particles to collide with the parachute, so therefore more of the gas or dust is displaced. So because we know that momentum is mass times by volume, there's a greater change in the momentum of the system because our mass is now bigger. So therefore we've got a greater change of momentum, or you could say greater work done, so therefore we need a greater resultant force on the system. Right, let's have a look at our next question. Figure 3 shows a golf ball at rest on a horizontal surface 1.3 meters from a hole. A golfer hits the ball so that it moves horizontally with an initial velocity of 1.8 meters per second. The ball experiences a constant deceleration of 1.2 meters per second squared as it travels to the hole. Calculate the velocity of the ball when it reaches the edge of the hole. So pause your video now, then unpause the video when you want to go through your answer. Right, so when you answer these types of questions, it's important to note, okay, it says it's a constant deceleration. So when you've got a constant deceleration or constant acceleration, you have to use the equations of motion, or SUVAT. So therefore what we can do is we can pop down what we know. So what do we know? We know that in this particular question that the acceleration A is going to be minus 1.2 because it's decelerating. We know that the initial velocity U is 1.8 meters per second. We know that the distance travelled S is 1.3, and we want to work out V, the final velocity. So we look at our equations of motion and realise we can use V squared equals U squared plus 2AS. Again, remember that A must be a minus value because it's decelerating. You pop your numbers in and you get 0.35 meters per second. Let's have a look at our next question. Later, the golf ball lands in the sandpit. The golfer hits the ball, giving it an initial velocity u at 35 degrees to the horizontal. The horizontal component of u is 8.8 meters per second. Show that the vertical component of u is approximately 6 meters per second. Then the ball traveling horizontally as it reaches x is shown. Assume that the weight is the only force acting on the ball when it's in the air. Calculate the time for the ball to travel to x. So pause your video now, then unpause your video when you want to go through your answer. Right, so in this first question, what can you do? Well, there's a number of ways in which you can work out the vertical component of a resultant force that you're given, or you can actually use it from the horizontal component that you were given. So what you could do is you could say that tan is equal to opposite over adjacent. Now in this triangle, we would know that opposite is going to be the vertical velocity, and then you could work it through that. Or how I would tend to do it is I would say, well, the horizontal component of u is u cos angle, and that equals 8.8. So what I would then do is I could then use that to work out what u is. So I would say u is equal to 8.8 over cos 35. That gives me the value of u, and then I would say, well, the vertical component of u, uv, is equal to u sine 35. Now remember, if you're always giving the angle to the horizontal, in most cases, okay, the horizontal component is going to be the cos of the angle, and the vertical component is the sine of the angle. So you get your answer through to be 6.2 meters per second. Now in our second question, what do we know? Well, if the only force acting on the ball is weight, well therefore it's acting as a projectile. So therefore what we can do is we can use our equations of motion. So once again, what do we know? Well, we know that when it reaches x, okay, that it's going to have a velocity of 0, so v is going to be equal to 0. We know u because we've got the horizontal and vertical components. Now again, I would suggest, okay, it says it's traveling horizontally as it reaches x. That indicates it's not traveling vertically. So we can say that in the vertical, the final velocity is equal to 0, and we've got the vertical component, which is u here, which we can say to be 6.2 meters per second. Okay, and at this point, we know that the acceleration is minus 9.81. We know this because it's going against gravity, which is going to be a 9.81. Okay, so what we can then do is we can use that to work out t, because you know v equals u plus at. We work it through to be 0.63 seconds. Right, let's have a look at the next question. The golfer returns the ball to its original position in the sandpit. He wants the ball to land at x, but this time with a smaller horizontal velocity than before. Sketch on this figure the possible trajectory for the ball and explain your reason for selecting this trajectory. So pause the video now, then unpause the video when you want to go through your answer. Right, so let's have a look at your answer. So what we need to do is as follows. So the first thing to consider is what's our trajectory of the ball going to be. Well, it's going to be a smooth curve because we know that it's curving upwards due to the effect of the actual motion like such, with the maximum turning point, and it starts and finishes at x, so it should be quite parabolic in shape as such, like that. Now why would you choose this particular trajectory? Well, if you increase the angle to the horizontal, the ball must go higher, so the ball must have a greater initial vertical velocity, or you could say that therefore it'll cover the horizontal distance over a longer time, so therefore it'll have a smaller horizontal velocity, so therefore that value of v will go down. Right, let's have a look at our next question. A student investigates moments by suspending a 100 centimeter ruler from two force meters A and B. A and B are attached to the ruler 12 centimeters from each end. Their supports are adjusted to make A and B vertical and the ruler horizontal. So the ruler is uniform and weighs 1.12 newtons. Determine the reading on A. Then the student suggests that the force exerted on the ruler by A and B act as a couple. Suggest whether his suggestion is correct. Right, so pause the video now, then unpause the video when you want to go through your answer. Right, now the first thing you've got to remember is if you've got a suspended system and you're looking into moments and it's at equilibrium, there's two things you can remember. That the moments clockwise and anti-clockwise equal each other, but also the forces acting up and the forces acting down are equal to each other because it's in equilibrium. Now, what we know is that the force acting down is 1.12 newtons, so therefore the total force acting up must be 1.12 newtons, but there's two force meters, so it's divided between the two, so you get our answer to be 0.56 newtons. Now, it's suggesting that forces exerted by A and B act as a couple. Well, what is a couple? Well, a couple are two forces which act in the same plane, have the same size, but they act in opposite directions because it causes rotation. Now, if we look at this situation, it's not a couple because they are two equal forces, but they're both acting in the same direction, upwards. So it can't be a couple because they're not acting in opposite directions. Right, so the student hangs a mass of weight W on the ruler between A and B as shown in the figure. He adjusts the supports that A and B are again vertical and the ruler is horizontal. The mass hangs at a distance d from A, so the reading on A is 0.82 newtons and the reading on B is 0.62 newtons. Determine W, determine D. So pause the video now, then unpause the video when you want to go through your answer. Right, so when you're doing these types of questions, again, there's two things you've got to remember. The forces acting up is equal to the forces acting down. Now we know straight away, and also, the moments clockwise equal the moments anti-clockwise. So we can work out what W is quite quickly, because we know from the previous question that there's a weight acting downwards of 1.12 newtons, and we know there's a force of W acting down. We also know going upwards, it's 0.82 newtons and 0.62 newtons. So you equate them. So you say the total upward force equals the total downward force. So therefore the force of W must equal to 0.32 newtons. We then use the principle of moments to work out our particular answer. Now, the easiest way to do this is take the moment about a point and consider, okay, where that point is. So you would then, and also remember when you're doing this, that you've also got to consider the actual moment due to the weight, which is found in the dead center of the ruler with a force of 1.12 newtons. So remember, to work out a moment, it's force times by distance. So you work out the clockwise moments and the anti-clockwise moments, and we say that a moment is force times by distance, and with that you can work out the distance of the object from A. Now, because we're working out the distance from A, it's probably best to take the moments from A as well. So you can do that and you get an answer to be 0.14 meters. Let's have a look at the next question. A river flows from west to east. The velocity of the current in the river varies from 0.2 meters per second near the banks to a maximum of 0.65 meters per second in the middle of the river. The current is always parallel to the bank. A girl swims from A and aims due north. Her speed relative to the water is a constant 1.1 meters per second, so that the magnitude of the girl's maximum resultant velocity is approximately 1.3 meters per second as she swims across the river. On different occasions, the girl swims in the direction with a speed of 0.90 meters per second relative to the water and with a variety of directions. State the magnitude and direction of the minimum possible resultant force that the girl can have. So let's have a look, okay, if you pause the video now, and then we'll have a go at answering that particular question. So the first thing to note is that when you're trying to work out the resultant velocity, okay, and it's got a horizontal and vertical component, well, you've got to use Pythagoras, and the resultant's going to be the resultant squared is equal to the horizontal squared plus the vertical squared. Now it's saying the maximum resultant velocity. Now you're given two values for the horizontal velocity here, but because you're working out the maximum resultant, you need to use the maximum horizontal. So it would say that the maximum horizontal squared is equal to 1.1 squared plus 0.65 squared, so you get an answer of 1.28 meters per second. Now in the next one, it says that she could swim in any direction with a speed of 0.90 meters per second. What's the minimum possible resultant force the girl can have? Well, if you have them in two opposing directions, they'll always add to give a value bigger. Okay, so the only time you're going to get the lowest possible value is when they're in the same plane and one's acting in the complete opposite direction to the other. So the minimum possible resultant force the girl can have is going to be the 0.90 minus 0.65, which is going to be the in the middle there in the opposite direction, so therefore she'd have to be swimming against that, which is due west, so therefore your answer is 0.25 meters per second. Let's have a look at the next question. Figure 2 shows a gymnast standing in equilibrium on a uniform beam, 3 meters from one end. The beam is 5 meters long and supports R and S are 0.50 meters from each end. The weight of the beam is 700 newtons and the gymnast has a weight of 470 newtons. Fs is the force exerted by S on the beam. By taking moments about X, calculate the magnitude of Fs. So calculate to pause the video now, and then we'll look at how you calculate your answer. Right, so how do you calculate this answer? So it's very important that you've got to take you've got to work out the moment of each force and then equate them where needed. Now the first thing to note is we're taking moments about X, so we don't need to consider the moment created by the reaction force of X, because the distance, which you remember moments are force times by distance, the distance is 0 from X, it's at X, so therefore any moment by the force produced by the support X is going to equal 0. So we can work out what our moment is from our gymnast, because it's going to be 470 times by 2.5. Now that's acting clockwise. Now the other thing that's acting clockwise is the actual moment produced by the weight of the beam. Now we know the weight of the beam is 700 newtons, it tells you in the question, and we know that its distance from X is going to be 2 meters. We know that because the weight is assumed to act directly in the middle of the object, so 2.5 meters from the end, because it's total 5 meters, so therefore from X it's 2 meters away. Now in the other direction we've got Fs, which we can see is going to be, if you look on the values here, it's going to be 2 meters away itself, so therefore, sorry, 4 meters away by looking away. So what we can say is 2 times by 700 plus 2.5 times by 470 equals 4 times by Fs. So we can then rearrange it, make Fs the subject, and we get 640 or 644 newtons. Let's have a look at the next question. An archer fires an arrow at an angle of 1 degree above the horizontal towards a target. The target is 25 meters away from the point of the arrow when it's fired. The arrow hits the target 0.20 seconds after it's fired. The lift force and drag force are negligible during the flight of the arrow. First, you show that the initial vertical component of the velocity of the arrow is approximately 1.7 meters per second. Then the center C of the target is at the same height as the point from which the arrow was fired. The arrow hits the target at point P. Determine the vertical displacement of P relative to C. So pause your video now, then unpause the video when you want to go through your answer. Right, in our first question, what do we know? Well, we know that the vertical value here, so the horizontal, that was looking for the vertical component of the velocity. Okay, well, what are we aware is that we know that the vertical height is going to be 25 meters over 0.260, because we know that it's going to be distance over time. Sorry, the horizontal one there. So therefore we can see that it's going to equal to 96 as shown before, which you can then lead it to be 1.678 as you can see before. Now the next one, how do you work out your value through? Well, again, we know that in this case, because the drag force and the lift force are negligible, there's only going to be one force acting on the object. So we can use projectile theory, so we can use the equations of motion and we can see what values that we've got. So we need to work out what S is, but we have been given T. It's 0.60 seconds. We know what A is going to be, because again we know that the only value is going to be gravity there, so as a result we know it's going to be minus 9.81. We know what U is because we've looked at in the previous question, and we know what T is, so we can say S equals UT plus a half AT squared, pop our numbers in, and we get an answer to be 0.10 or 0.11, so therefore it's between 0.10 meters and 0.11 meters above the center of the target, because you can see in the direction which it's been aimed at. Right, let's have a look at our next question. A student places a wooden block on a ramp inclined at 30 degrees to the horizontal as shown in the figure. The block is pulled up by the ramp by a light inextensible string connected over a frictionless pulley to an object of mass 0.4 kilograms. The object is initially held at rest 0.45 meters above the bench. The wooden block has a mass of 0.25 kilograms and is initially at rest. The object is released and accelerates vertically downwards at 2.23 meters per second squared. Explain two ways in which the momentum of the object is different from the momentum of the wooden block during this acceleration, then calculate the tension in the string as the object accelerates. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this first question? Well, we know straight away that the magnitude of the momentum of the block is going to be smaller than the momentum of the object. We can tell this because of how much is actually being moved, okay? And then finally that the two momentums, are going to be in different directions, because you'll notice that one's going in one direction, one's going in another direction. Momentum is a vector, so another difference is they're moving in different directions. Now, how do you calculate the tension in the string? So it's important to note that if you look at the situation, the object is pushing down on the string and producing a force of mass times by acceleration, because F equals ma, it's accelerating downwards, so we can say the force produced is ma. But what about in the other direction? Well, we've got our tension acting in the opposite direction, but also it's important to note that in the same direction as the object falling is going to be the weight of the object, because it's already acting downwards. So therefore we can say that T is going to be equal to ma plus mg. So when we work that through, we can put our values in and we can see that we get to be tension is equal to 3 newtons. Right, let's have a look at this question again. So we've got the same ideas here, that the object is initially held at rest 0.5 meters above the bench. The wooden block has a mass of 0.25 kilograms as initially at rest. The object is released and accelerates vertically downwards at 2.23 meters per second squared. Show that the object is traveling at approximately 1.4 meters per second before it hits the bench. Calculate the component of the weight of the wooden block that's parallel to the ramp. And then when the object hits the bench, the string becomes slack and the wooden block decelerates and stops. There's a constant frictional force of 1.25 newtons between the wooden block and the ramp. Calculate the distance the wooden block travels parallel to the ramp as it slows down. So pause your video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? Well, in the first question, again, we know that it's accelerating at a constant speed. Okay, also the constant rate, which is 2.23 meters per second. So we can therefore once again use a Suvat equation. So we've got to think we want to work out what v is, which is our final velocity. We know what u is because we know that's initially held at rest. So u is going to equal 0. We've got our acceleration and we've got our displacement when we move in this particular direction in the vertical. So we can say v squared equals u squared plus 2as. We pop our values in and we get an answer for v of 1.42 meters per second. So when we're trying to calculate the component of the weight of the wooden block that's parallel to the ramp, well, straight away when we look at our situation, we can see that when we're given this particular triangle of forces, that the component of the weight parallel to the block is going to be sine angle. So we do the weight sine 30, so we work through to be 1.23 newtons. Then finally calculate the distance the wooden block travels parallel to the ramp as it slows down. Well, it's important to note that we're going to add our frictional force to the component of the weight parallel to the slope because they're both acting to slow it down. So therefore we do 1.25 newtons plus 1.23 newtons. That's going to be the frictional force which we're told in the question before, and added onto the parallel component of the weight because they're both acting to slow it down. So therefore we can say that work done is force times by distance. So therefore we can work out what the work done is because we can say it's the change of the kinetic energy. So we do a half mv squared to work out our work done. We've got our force because we've just worked it through. So therefore we can work out our distance because the distance is going to be the work done, which is a half mv squared, divided by our force, which we've just worked out before. So we get our distance to be 0.10 meters. Let's have a look at our next question. A wing screw is tightened using a thumb and a finger. The thumb and the finger each apply a force F as shown in the figure. Explain why the forces shown are act as a couple. Then the perpendicular x between the lines of action of the force is 3.2 centimeters as shown in the figure. Calculate the force required to reach a couple of 1.2 newton meters. So pause the video now, then unpause the video when you want to go through your answer. Right, so why is this a couple? Well, we've talked about this before. What is a couple? A couple is when you've got two forces equal in magnitude in the same plane but in opposite directions. Then what's the value of the F going to be? Well, straight away, how do we work out the force? Well, we know that moment is going to be force times by distance. So therefore, our force is going to be the moment divided by the distance between the two objects. Now again, what's our distance? 3.2 centimeters. Convert that into meters, so it's 0.032 to get our answer to be 37.5 newtons. Let's have a look at the next question. Figure 5 shows a child on a sled sliding down a slope. The total mass of the child on the sled is 75 kilograms. She starts on rest at A and descends to a vertical height of 5.5 meters to B. First, you state how to calculate the work done by a force, then show the speed of the sled at B with approximately 10 meters in the absence of friction. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you work out work done? Well, we know that work done is equal to force times by distance, but that's not the complete equation because it's actually force times by displacement. So it's force times by the distance travelled by the object in the direction of the force. Now you could also say that this is F times by S times by cos theta, because again S cos theta gives you the direction in the direction motion in the direction of the force. Now, next one, show that the speed of the sled at B would approximately be 10 meters per second in the absence of friction. So again, what do we know? If you look in the situation, we're starting off, we're sliding down a slope, so we're starting with gravitational potential energy, we're turning that into the kinetic energy, so therefore we can say mgh is equal to a half mv squared. You can cancel the m's through because they're equal on both sides, so we can say gh is equal to a half v squared. Therefore we can pop our numbers in because we know g to be 9.81, we know h to be 5.0, 10.5 meters, and we know a half v squared on the other side, so we can rearrange it, make v the subject, and we get 10.4 meters per second. Let's have a look at our next question. So figure 5 shows the same child. The actual speed of this letter B was 5.8 meters per second, and the distance travelled from A to B is 17.2 meters. Calculate, using energy considerations, the average frictional force experienced by the sled. So pause the video now, then unpause the video when you want to go through the answer. Right, so how can you do this? So what you would do is the same as before. You'd work out your potential energy at the start, so by doing mgh. You would then do your kinetic energy, which is a half mv squared, so therefore you would work it through as such. Now then what you want to do is find the difference between the two energy stores. Now we then know that force is equal to work done times by distance travelled, so therefore once you've then done that, we can say that the frictional force is equal to the work done over the distance. Now the work done in this case is the difference between the two energy stores, because it's the work done by friction to transfer the energy from the object to the surroundings. So say friction is equal to work done over distance, and we then get our frictional force. Right, let's have a look at our next question. So figure 4 shows a golf ball hit from a mound of height 12 meters. The initial velocity of the ball is 48 meters per second at 15 degrees to the horizontal. The golf ball takes 3 seconds to reach a position at a vertical height h above the hole. D is the horizontal distance from the point where the ball is hit to the hole. Okay, ignore the effects of air resistance for this question, calculate D. So pause the video now, then unpause the video when you want to go through your answer. Right, so how would you answer this particular question? So you've got to calculate D, which is the horizontal distance. Now it's important to note that in this situation, okay, that the only force acting on the object is going to be weight, which is in the vertical. That's one of the conditions of a projectile, and we can say that there's no air resistance in the question, so it must be acting as a projectile. So this tells us that the only force acting on the object is in the vertical. So in the horizontal, there's no force acting on the object. So at this point, the object will have inertia in the horizontal. Now when an object has inertia, you can just use a simplified equation that velocity is equal to displacement over time. So at this point we can say, well, what we're going to do, we want to work out the horizontal displacement, so therefore we can say that it's going to be the velocity times by the time. Now the next thing to note is we need to know what the horizontal velocity is. Now you're given the resultant velocity, 48 meters per second, but we need to find the horizontal component of that. Now once again, you've been given the angle to the horizontal, so the quick way you can work out the horizontal is it's the resultant cos of the angle. So we say the horizontal velocity is 48 cos 15, so we get 46.4 meters per second. So therefore the horizontal distance is the horizontal velocity times by the time, because we've got inertia. So therefore it's going to be 46.4 times by 3 is 139 meters. And the last thing you should always do in these questions is check your answer to see if it sounds right. And a golf ball traveling 140 meters sounds like it would be appropriate, so it's most likely to be right. So that brings an end to our revision session today. If we've been successful in this revision session, we should be able to answer A-level physics questions on mechanics, assess our understanding on mechanics, and then understand what topics in mechanics we need to improve on for AQA A-Level Physics. So thank you very much for watching this revision session on mechanics. Okay, thank you very much and have a lovely day. Hello and welcome to this revision session for mechanics, which is part of the revision sessions for AQA A-Level Physics. So in today's revision session, we're going to look at answering examination questions on A-Level Physics, and in particular the mechanics topic. So if you've been successful and learnt in this particular revision session, you should be able to answer A-Level Physics exam style questions, assess your understanding of A-Level Physics, and understand what topics you need to improve upon for A-Level Physics. So let's look at how you should prepare for this revision session. Firstly, when completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than that of the right hand side, and in this left hand side section write down your working out and answers to the questions in the revision session. And when you're doing this, make sure you write your answers in full sentences and show your full working out. Whilst on the right hand side in this section, write down any piece of information which you find useful or any hints and tips on answering questions from this revision session. And at the end of the revision session, write up these notes into a revision sheet for you to use independently. So how should you be revising AQA A-Level Physics? So the first step is learning the key facts. So use your revision guide, your class workbooks, your student prep notes, your textbook to learn the key ideas of the course. And you may wish to make mind maps or notes to do this yourself. Then second step is to test yourself. So use Caboodle, use Seneca, use knowledge checkers to quickly test your own knowledge, and you may wish to do this from your own cue cards. Then finally, step 3 is use examination preparation books, homework books, supervised study books, additional workbooks to practice examination questions and then mark your own work. And you may even wish to download your own exam past papers to do this. So the combination of learning the key facts, then testing yourself, then practicing exam style questions is the way and how you should be revising AQA A-Level Physics. So let's have a look at a few questions for mechanics. The first question states, Figure 3 is an identical velocity time graph for an object oscillating about a fixed point. Determine using Figure 3 the maximum acceleration of the oscillating object. So pause the video now, then unpause the video when you want to go through your answers. Right, so how do you answer this question? Well, you've got to be aware that the gradient of a velocity time graph is the acceleration, but you've got a curve. So how can you work out the gradient of a curve? So what you would do is draw a gradient, okay, by drawing a tangent to the curve on the graph. Then you can use this gradient of the tangent to then work out your acceleration. Now again, you want to do your maximum acceleration, so you're looking at where the gradient, okay, is the highest, so where the line is at its steepest, and you should be getting between an answer of 15 to 20 meters per second. The next question says, now figure 4 is also a velocity time graph for an object oscillating about a fixed point. Determine using figure 4 the maximum displacement of the object from the fixed point. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, you've got to be aware that to work out the displacement of an object, you've got to be working out the area under the graph. But it's important to note that if it's below the graph, below the x-axis, it's going to be a negative value, and above the x-axis is going to be a positive value, because you want to work out displacement and not distance travelled. So what you would do is you would determine the area under the graph, so you can work out what each square is equal to, and then you can count the number of squares. Then you can work out your answer to be 2.3 times 10 to the minus 3, or to 2.7 times 10 to the minus 3 meters. Our next question says, a tennis ball is served horizontally as shown in figure 5. The bottom of the ball is 2.75 meters above the ground and the horizontal distance of 11.9 meters from the net. The top of the net is 1.07 meters above the ground. Assume air resistance is negligible in this question. So show that the time taken for the bottom of the ball to fall to 1.07 meters above the ground is approximately 0.6 seconds, and then calculate the minimum initial horizontal velocity which the ball must have to get over the net. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, what you can do here is, because you know it's falling vertically and the only force that is acting on it is gravity, you've got a constant acceleration, so you can use suvat. So we can use suvat to show that our answer for t, so it is about 0.6 seconds. So what we can do is we can say s is equal to ut plus a half at squared. We know that a is going to be the acceleration due to gravity because it's falling downwards, so a is going to be 9.8, and then you can say we know that s, the displacement, is the difference from in the height to fall to the ground, so it's 1.07 meters. Okay, you can work out through that, so you can see that it's going to be working through from 2.75 to 1.07. You can work out your difference as the distance to fall. So you've got s, you know what your value of u is going to be. It's going to be 0 because it's starting off at is a stationary, so therefore we know u is 0, so we can say that s is equal to a half at squared. So therefore we can work it through. Okay, and then you can get your answer to be 0.585 seconds. Now the next question is, well, at this point calculate the minimum horizontal velocity the ball must have to get over the net. Well, what we can say is in the horizontal we know what our displacement is going to be. You can see in the questions 11.90. We know what our time is because you just worked it out to be 0.585. Please remember in SUVAT that the only quantity which can be transferred between horizontal and vertical is the time, and therefore we can say speed is going to be equal to distance over time, so therefore, or velocity is displacement over time, so therefore we can say that the displacement, okay, is going to be 11.90. We can say that our time is 0.585, so our answer is 20.3 meters per second. Now again, it's very important to note that we can use the equation velocity as displacement over time, because in the horizontal there are no forces act on the object, so it has a constant velocity, so we can use that particular equation. The next question says, later in the game, the ball has a horizontal component of the velocity of 42 meters per second and a downward vertical component of the velocity of 26 meters per second. Determine the resultant velocity of the ball. You may use a calculation or a scale diagram. So pause the video now, then unpause the video when you want to go through your answer. Right, so how would you answer this particular question? Well, if you wanted to do a calculation, you should use Pythagoras. So what you can do is you know already what the horizontal component of the velocity is going to be. It tells you in the question it's 42. You know that the downward vertical is going to be 26, so we can then draw that out as a right angle triangle. So therefore we can say the horizontal component squared plus the vertical component squared is equal to the overall component squared. Work it through and then work out your answer to be 49.4 meters per second, and then you can use your appropriate trigonomic relationship by doing either sine is going to be opposite over hypotenuse, cosine is going to be adjacent over hypotenuse, or tan is going to be equal to opposite over adjacent to work out your angle, which is 32 degrees. The other way in which you can do that is to draw a scale diagram. So again, draw your right angle triangle to scale, so you can look at the values and scale them correctly. At that point you can then draw in your resultant force by joining up the two lines at right angles. You can then measure it with a ruler and convert back to scale and measure the value with a protractor. The next question says, Figure 8 shows a section of a suspension bridge. The bridge deck is supported by a single cable attached to a vertical tower. Figure 9 is an enlarged view of the cable and the top of the tower. The cable makes an angle of 40 degrees to the horizontal where it meets the tower. The tension T in each section of the cable is 1.2 times 10 to the 8 newtons. The weight of the cable is negligible. Calculate the magnitude of the resultant force exerted on the tower by the cable. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? So we need to calculate the magnitude of the resultant force exerted on the tower by the cable. Now you'll notice that we're going to have to then work out the component, because if we look on the question we need to be thinking about the vertical, because the tower is in the vertical of the cable, so it needs to be the vertical component of the force acting on the cable. So therefore we can do either T sine 40 or T cos 50 and work out our answer to be 1.5 times 10 to the 8 newtons. It's always very important that when you're given a force at an angle, you can work out the horizontal and vertical component of the force and work out which one is relevant, which one is useful to that situation. The next question says, for the same particular suspension bridge, the mass of the tower is 7.1 times 10 to the 6 kilograms. Calculate the magnitude of the reaction R of the ground on the base of the tower. So pause the video now, then unpause the video when you want to go through your answer. Right, so what do we know here? Well, we know that when we've got a reaction force acting upwards, we know that there must be a weight acting downwards from the tower onto the ground, okay, which is of equal size to that reaction force. So what we can say is pretty much that the magnitude of the reaction force is equal to the magnitude of the weight of the tower. So what you would then say is you say we've got our mass, which is 7.1 times 10 to the 6 kilograms, and then we convert that into the weight by doing 9.81 times by that mass, and then you can add the weight of the tower to the value from the previous question, and there's our overall value of the reaction force. Our next question says, a car of mass 1,400 kilograms starts from rest and travels along a horizontal road for 90 meters. Figure 10 shows the variation with distance of the resultant force on the car. Describe the motion of the car over the 90-meter journey and calculate the initial acceleration of the car. So pause the video now, then unpause the video when you want to go through your answer. Right, so it's important that you can be able to understand how resultant force can link to the motion of an object. So you should be aware that the resultant force is directly proportional to the acceleration of the object. That is Newton's first and second law of motion. So what we can therefore say is on our graph, our resultant force is increasing. So therefore our acceleration is also increasing. So therefore calculate the initial acceleration of the car. Now we know that F equals ma, that's Newton's second law of motion, so therefore A is equal to F over m. So we can work out our resultant force by working out the value from the graph. We can then divide it by the mass, which is given in the question. Now do remember that we're going to be using the resultant force in kilonewtons, so convert that into newtons. So 4.4 kilonewtons will become 4,400 newtons. So you can work that through and you can get your answer out. Now again, it's important to note the initial acceleration of the car. So the initial means at the start. So in this question, the resultant force at the start is 0.2 kilonewtons. So therefore it will be 200 newtons. So you'll be doing 200 divided by 1,400 to get 0.143. Right, our next question says, for the same particular graph, show that the useful work done accelerating the car over the 90-meter journey is about 2 times 10 to the 5 joules. Then calculate the speed of the car after it has travelled 90 meters. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, you should remember that work done is equal to force times by distance. So therefore, this tells us that for a force distance graph, that our area under the line is going to equal work done, because the y-axis times by the x-axis is actually the area under the line. So the work done is the area under the graph. So what you can do is you can work out the right angle triangle. Now please remember from the question, it doesn't start at 0, it starts at 0.2. So when working out your y value, you're going to do 4.4 minus 0.2, then times by 10 to the 3 because it's in kilonewtons. We then divide it by our value of 2 because it's a half AB. So for the area of a triangle, so you divide it by 2 and then you multiply it by the height of the the distance value, which is 90. So you would do 0.2 plus 4.4. Okay, so you work it through to find your difference there, times by 10 to the 3, divided by 2, times by 90, and we get 2.07 times by 10 to the 5. Now the next question says, calculate the speed of the car after it has travelled 90 meters. Now the trick to this question is that we've just worked out the work done. Now the work done is going to be transferring energy from the previous energy store into the kinetic energy store because it's making the car go faster. So we can say our work done is equal to kinetic energy, and kinetic energy is equal to a half mv squared. So from our value of work done, we know that that's kinetic energy store. We've got our value of mass from the previous part of the question, so you can work out V, and that's 17.2 meters per second. Figure 4 shows a golf ball hit from a mound of height 12 meters. The initial velocity of the ball is 48 meters per second at 15 degrees to the horizontal. The golf ball takes 3 seconds to reach a position at a vertical height h above the hole. D is the horizontal distance from the point where the ball is hit to the hole. Ignore the effects of air resistance for this question. Calculate D. So pause the video now, then unpause the video when you want to go through your answer. Right, now as mentioned before, because we know in the horizontal, okay, because that's what we're going to be working out here, okay, we can just use the equation distance is equal to the velocity times by time, because in the horizontal there's no forces acting on the object, because the only force acting on this object is weight, which is in the vertical, and vertical and horizontal forces do not interact or affect each other. So therefore in this situation there's no horizontal forces acting on the object. So therefore we can just use the equation velocity is equal to displacement over time, so therefore displacement is equal to velocity times time. The only trick you've got to do for this question is that you've got to remember that you've got to be using the horizontal component of the velocity. Now in this question you're given the resultant velocity, so you've got to convert 48 meters per second at an angle of 15 degrees to a horizontal component. So it's 48 cos 15. You can work that out by drawing a right angle triangle of your information. So therefore we get 46.4 times it by our time, which is 3 seconds from the question, so it's 139 meters. Now this next question says, show that the initial vertical component of the ball is approximately 12 meters per second, and then calculate h. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this particular question you've got to be aware that in the vertical there is a resultant force acting on the object, and that is weight, and it's a constant resultant force, so therefore we've got a constant acceleration acting on our object. So with a constant acceleration we can use SUVAT. So with SUVAT what we can say is as follows. We can say that we can work out our overall value of h by doing s is equal to ut plus a half at squared. But firstly in part 2 we've got to work out our initial velocity, okay, in the vertical. So in that case, whilst the horizontal was 48 cos 15, the vertical is 48 sine 15. Now it's important to note in this particular situation that work out which one is sine and which one is cos for the vertical and the horizontal. You draw a right angle triangle of the situation, and you can then use the trigonomic identities that sine is equal to opposite over hypotenuse, cosine is equal to adjacent over hypotenuse, and tan is equal to opposite over adjacent to work out which particular trig identity goes with horizontal and vertical. So when you've got your vertical velocity, we can then use that in our SUVAT equation. Why using SUVAT? Because we've got constant acceleration. And remember, because it's falling down, our acceleration is going to be minus 9.81 because it's going down, so it's going against gravity. So you pop your numbers in for u, because you know it's 12.4 from the previous question, times by the time given, which is 3, plus a half, times by our acceleration, which is minus 9.81, multiplied by time squared, which is 3 squared, so our answer is minus 6.9. So when we start our answer off at 12 and it's lost 6.9, so therefore it's now at 5.1 meters. Our next question says, figure 5 shows a child on a sled sliding down a slope. The total mass of the child and the sled is 75 kilograms. She starts from rest at A and descends to a vertical height of 5.5 meters to B. Firstly, state how to calculate the work done by a force, then show that the speed of the sled at B would approximately be 10 meters per second in the absence of friction. So pause the video now, then unpause the video when you want to go through your answer. Right, so how to answer this particular question? Well, we've got to remember that work done is equal to the force times by the displacement, or the force times by the distance travelled in the direction that the force is acting in. Now in this next question, we're going to be, by the fact that it says there's an absence of friction, we can assume that at this point that all of the potential energy store at the start of the slope is going to convert into the kinetic energy store as the sled reaches the bottom. So we can say mgh is equal to a half mv squared. We can then cancel out our values of m on each side and say gh is equal to a half v squared. We have g, 9.81. We have h from the question, 5.5, and therefore we can work out what our value of v is going to be. So that answer is 10.4 meters per second. The next question says the actual speed of the sled at B is 5.8 meters per second. The distance AB is 17.2 meters. Calculate using energy considerations the average frictional force experienced by the sled. So pause the video now, then unpause the video when you want to go through your answer. Right, so how to answer this particular question? So what you would do is you could work out your predicted kinetic energy. So what you would say is the predicted kinetic energy is a half times by mass times by the velocity squared. Now in the previous question we'd worked out what that velocity should be, which is 10.4 meters per second. So we can work it out that it's going to be 4,056 joules. We can then work out what the actual kinetic energy is by doing a half times by mass times by the actual velocity squared, which is 5.8. So we get our true kinetic energy to be 1,261. So therefore the work done due to friction must actually be the difference between the two values. So it's 4,056 minus 1261. So that's going to be our work done due to friction. We can therefore say force is equal to work done divided by distance or displacement, because we know that work done is force times by displacement. So therefore we can divide that value by 17.2, and that works out our frictional force to be 160 or 162 newtons. Now again, it's very important to remember that we can work out the work done due to friction by working out what the kinetic energy should be and subtracting from what the kinetic energy actually is. The next question says, state the principle of moments. Then figure 1 shows a uniform beam of length 3.2 meters and a mass of 27 kilograms. The beam is placed with one end against the bottom of the wall at X. A person holds the beam at 35 degrees to the horizontal by applying a force F to the other end of the beam. F is applied at right angles to the beam. Determine F by taking moments about X. So pause the video now, then unpause the video when you want to go through your answer. So it's important that you can be able to actually talk about what the principle of moments are and how you can then determine values with them. So this first question is all about just rote knowledge. What is the principle of moments? And the principle of moments is the idea that there is no resultant moment, or that you say that the sum of all the clockwise moments equals the sum of all the anti-clockwise moments when a body is in equilibrium. Now technically when a body is in equilibrium, we know that there's no resultant moment and there's no resultant force acting on the object. So what you can say here is if you take moments about X, you know that the resultant moment is going to equal 0. So we can say that the clockwise moment equals the anti-clockwise moment. So what we can say is that force times by distance clockwise equals force times by distance anti-clockwise. So what you can then do is therefore you can work out what the moment of the weight is by doing force times by distance. Now you know that the mass is 27, so therefore you can do 27 times by 9.81 times by 3.2. But also just be aware that we're going to take our component working through as well. So we can say working through to be 2 times by cos 35 by looking at the angle, so therefore that equals 347 newton meters. So what we can therefore say is that on the other side, therefore force is equal to moment divided by the distance, because we can look at our equation working through and say moment is equal to force times by distance, so therefore force is equal to moment over distance. So therefore we've got our moment on one side, so it's got to be the moment on the other side, so therefore we say it's 347. We then divide it by 3.2 because that's the distance it is from the value of X, so therefore it's 110 or 108 newtons. Our next question says figure 2 shows a ball thrown with a velocity of 15 meters per second at an angle of 20 degrees to the horizontal. It reaches a wall 0.15 seconds after being thrown. Throughout this question, assume that air resistance is negligible and calculate the horizontal distance travelled by the ball. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? Well, once again, horizontally, we know that there's no resultant force acting on the object in that particular plane. So we can use our equation that we can say that we can do horizontal distance is going to be the horizontal velocity times by the time. So you know our time to be 0.15 seconds, and we can convert 15 meters per second at an angle of 20 degrees to a horizontal by doing 15 cos 20. Once again, draw out your right angle triangle showing that, and then work out which identity to use. And therefore we say 15 cos 20, which is 14.1, times by 0.15 is 2.1 meters. The next question says, so calculate the height h gained by the ball and calculate the speed at which the ball hits the wall. So pause the video now, then unpause the video when you want to go through your answer. So how do you calculate the height? Well, again, we can use suvat here because we've only got one force acting on the object, and that is gravity, so or weight, so therefore our acceleration is our acceleration due to gravity. We can work out our vertical component of the velocity because we're looking at how high it goes vertically by doing 15 sine 20, so we know that it's 5.13 meters per second. We can then find the correct suvat equation to use. S equals ut plus a half at squared. We know a is 9.1 because it's acceleration due to gravity. We're given t in the question to be 0.15, and we know what u is because we started out by saying it's 5.13 and worked it out to be 0.66. 1.66 meters. Now, how can you therefore work out the speed at which the ball hits the wall? Well, what you would do is you could use suvat to calculate the vertical velocity when it hits the wall. So we know what our value of u is, we know what s is, we know what t is, we know what a is. So we could say, for example, v is equal to u plus at, where u is equal to 5.13, a is equal to 9.81, and t is equal to 0.15. That's our vertical velocity, but it wants the overall velocity. Now again, it's important to note that for our horizontal velocity, because there's no resultant force acting on the object, the velocity will stay constant because the resultant force causes acceleration, so no resultant force will lead to inertia. So therefore we've got our value for the vertical velocity, our value for the horizontal. We can use Pythagoras by saying the resultant is going to be the resultant squared is equal to the vertical component squared plus the horizontal component squared. So it's going to be 3.65 squared plus 14.1 squared, all square rooted, which is 14.6 meters per second. The next question shows figure 3, which shows a sphere that falls through a distance h on the horizontal ground. The sphere hits the ground and rebounds. Figure 4 shows the variation with time of the velocity v of the sphere. So calculate the value of h. So pause the video now, then unpause the video when you want to go through your answer. Right, so how would you calculate h? Well, h is going to be the displacement, which for the velocity time graph is the area under the line. So what you need to do is take the area under the graph between the time of t and 0.57 seconds. Why 0.57 seconds? Well, that's the point at which it's going to rebound and change direction because it's going to a negative, so that allows you to work out the height. So therefore we can work it out from the graph and do it to be the answer of 1.60 meters. Right, our next question says, calculate the magnitude of the acceleration of the sphere whilst it is in contact with the ground. Then the mass of the sphere is 58 grams. Calculate the force exerted by the ground on the sphere while it is in contact with the ground. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you work out this first particular question? Well, we're trying to work out acceleration. Now, on a velocity time graph, acceleration is equal to the gradient of the line. So you've got to work out the acceleration whilst the object is bouncing. And you can tell the bounce section, because if you look on your particular graph, you can tell that it's going from 5.6 to 3.6 or minus 3.6, so you can work it through that way. That's the bounce section because that's when it's doing that almost vertical line, and then we can work out our gradient that way to get 310 or 307 meters per second squared. It then says the mass of the sphere is 58 grams. Calculate the force exerted by the ground on the sphere whilst it's in contact with the ground. Now we do know that F is equal to ma, so therefore we've got our value of A from the previous question. We know our value of mass, which is 58 grams, which is going to convert to kilograms. So we can work it through, and then we can also say that weight is equal to mass times by gravity, and we know the value of the mass again, we know our value of gravity, and we can add the two together. Now remember, why do we have to add both of them together? Well, we can do that because we've got the force exerted on the ground just to the movement, which is F equals ma, but we've also got the force exerted on the ground by the sphere due to its weight. So you've got to think of all the force acting on it when it's in contact with it. So you add the two together and you get 18.4 newtons. Our next question says, okay, here that we've got another sphere of the same radius but much less mass is dropped from the height h onto the ground. For the sphere, air is insignificant during its descent. Sketch on figure 4 a velocity time graph for this sphere and from time t equals 0 when it is dropped until it hits the ground for the first time. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, you've got to understand that the end of the new line or the curve is at a later time because it's obviously undergone air resistance during its descent, so therefore, okay, it's not going to hit the ground as quickly. And also, the gradient is going to be curving now, and not a straight line, because you've got to think of the factor of air resistance. Now, when air resistance is significant, the acceleration will decrease whilst the speed is getting bigger. The change of speed is getting less, so the curve is going to decrease in gradient now, and our maximum velocity is going to be lower because some of the kinetic energy has been dissipated to the surroundings with this air resistance. So I hope you've enjoyed this particular revision session on mechanics. If you've been successful and learned in this revision session, you should be able to answer A-level physics examination style questions, assess your understanding on A-level physics, and understand what topics you need to improve upon for A-level physics. So thank you very much for watching this revision session on mechanics, which is part of the AQA A-Level Physics specification. Thank you very much and have a lovely day.